7 years, 250 videos, and 100,000 subscribers later, I bring you this special. In this video, we are going to talk about transformer neural networks, from what they are, why they exist, to I can now build a transformer neural network from scratch using NumPy and PyTorch. If you're new here, hi, I'm Code Emporium. But if you're not new here, thank you all so much for supporting me over the years. Now let's get to learning some transformer neural networks.
Recurrent neural nets. They are feed-forward neural networks rolled out over time. As such, they deal with sequence data, where the input has some defined ordering. This gives rise to several types of architectures. The first is vector-to-sequence models. These neural nets take in a fixed size vector as input, and it outputs a sequence of any length. In image captioning, for example, the input can be a vector representation of an image, and the output sequence is a sentence that describes the image. The second type is a sequence-to-vector model. These neural networks take in a sequence as input and spits out a fixed-length vector. In sentiment analysis, the movie review is an input, and a fixed-size vector is the output indicating how good or bad this person thought the movie was. Sequence-to-sequence models is the more popular variant, and these neural networks take in a sequence as input and outputs another sequence. So, for example, language translation. The input could be a sentence in Spanish, and the output is the translation in English. Do you have some time series data to model? Well, RNNs would be the go-to. However, so slow that we use a truncated version of backpropagation to train it, and even that's too hardware intense. And also, they can't deal with long sequences very well. We get gradients that vanish and explode if the network is too long. In comes LSTM networks in 1991 that introduced a long short-term memory cell in place of dumb neurons. This cell has a branch that allows past information to skip a lot of the processing of the current cell and move on to the next. This allows the memory to be retained for longer sequences. Now, to that second point, we seem to be able to deal with longer sequences well. Or are we? Well, kind of. Probably of the order of hundreds of words instead of 1,000 words. However, to the first point, normal RNNs are slow, but LSTMs are even slower. They're more complex. For these RNN and LSTM networks, input data needs to be passed sequentially or serially, one after the other. We need inputs of the previous state to make any operations on the current state. Such sequential flow does not make use of today's GPUs very well, which are designed for parallel computation. So question, how can we use parallelization for sequential data? In 2017, the Transformer Neural Network architecture was introduced. The network employs an encoder-decoder architecture, much like recurrent neural nets. The difference is that the input sequence can be passed in parallel. Consider translating a sentence from English to French. I'll use this as a running example throughout the video. With an RNN encoder, we pass an input English sentence one word after the other. The current word's hidden state has dependencies in the previous word's hidden state. The word embeddings are generated one time step at a time. With a transformer encoder, on the other hand, there is no concept of time step for the input. We pass in all the words of the sentence simultaneously and determine the word embeddings simultaneously. So how is it doing this? Let's pick apart the transformer architecture. I'll make multiple passes on the explanation. The first pass will be like a high overview, and the next rounds we'll get into more details. Let's start off with input embeddings. Computers don't understand words. They get numbers, they get vectors, and matrices. The idea is to map every word to a point in space where similar words in meaning are physically closer to each other. The space in which they are present is called an embedding space. We could pre-train this embedding space to save time, or even just use an already pre-trained embedding space. This embedding space maps a word to a vector, but the same word in different sentences may have different meanings. This is where positional encoders come in. It's a vector that has information on distances between words in the sentence. The original paper uses a sine and cosine function to generate this vector, but it could be any reasonable function. After passing the English sentence through the input embedding and applying the positional encoding, we get word vectors that have positional information, that is context. Nice. We pass this into the encoder block where it goes through a multi-headed attention layer and a feed-forward layer. Okay, one at a time. Attention. It involves answering what part of the input should I focus on. If we are translating from English to French and we are doing self-attention, that is attention with respect to oneself, the question we want to answer is, how relevant is the ith word in the English sentence relevant to other words in the same English sentence? This is represented in the ith attention vector, and it is computed in the attention block. For every word, we can have an attention vector generated which captures contextual relationships between words in the sentence. So that's great. The other important unit is a feed-forward net. This is just a simple feed-forward neural network that is applied to every one of the attention vectors. These feed-forward nets are used in practice to transform the attention vectors into a form that is digestible by the next encoder block or decoder block. Now, that's the high-level overview of the encoder components. Let's talk about the decoder now. During the training phase for English to French, we feed the output French sentence to the decoder. But remember, computers don't get language. They get numbers, vectors, and matrices. So we process it using the input embedding to get the vector form of the word. And then we add a positional vector to get the notion of context of the word in a sentence. We pass this vector, finally, into a decoder block that has three main components, two of which are similar to the encoder block. The self-attention block generates attention vectors for every word in the French sentence to represent how much each word is related to every word in the same sentence. These attention vectors and vectors from the encoder are passed into another attention block. Let's call this the encoder-decoder attention block since we have one vector from every word in the English and French sentences. This attention block will determine how related each word vector is with respect to each other, and this is where the main English to French word mapping happens. The output of this block is attention vectors for every word in English and the French sentence, each vector representing the relationships with other words in both the languages. Next, we pass each attention vector to a feed-forward unit. This makes the output vector more digestible by either the next decoder block or a linear layer. Now, the linear layer is, surprise, surprise, another feed-forward connected layer. It's used to expand the dimensions into the number of words in the French language. The softmax layer transforms it into a probability distribution, which is now human interpretable. And the final word is the word corresponding to the highest probability. Overall, this decoder predicts the next word, and we execute this over multiple time steps until the end of sentence token is generated. That's our first pass over the explanation of the entire network architecture for transformers. But let's go over it again, but this time introduce even more details, going deeper. An input English sentence is converted into an embedding to represent meaning. We add a positional vector to get the context of the word in the sentence. Our attention block computes the attention vectors for each word. Only problem here is that the attention vector may not be too strong. For every word, the attention vector may weight its relation with itself much higher. It's true, but it's useless. We are more interested in interactions with different words. And so we determine like 8 such attention vectors per word, and take a weighted average to compute the final attention vector for every word. Since we use multiple attention vectors, we call it the multi-head attention block. The attention vectors are passed in through a feed-forward net, one vector at a time. The cool thing is that each of the attention nets are independent of each other, so we can use some beautiful parallelization here. Because of this, we can pass all our words at the same time into the encoder block, and the output will be a set of encoded vectors for every word. Now the decoder. We first obtain the embedding of French words to encode meaning. then add the positional value to retain context. They are then passed to the first attention block. The paper calls this the masked attention block. Why is this the case though? It's because while generating the next French word, we can use all the words from the English sentence, but only the previous words of the French sentence. If we are going to use all the words in the French sentence, then there would be no learning. It would just spit out the next word. So while performing parallelization with matrix operations, we make sure that the matrix will mask the words appearing later by transforming it into zeros, so the attention network can't use them. The next attention block, which is the encoder-decoder attention block, passed into the feed-forward layer, linear layer, and the softmax layer to predict the next word. That's the pass 2 over the architecture explained. I hope you're understanding more and more details here. Now for the next pass, where we go even deeper. How exactly do these multi-head attention networks look? Now, the single-headed attention looks like this. Q, K, and V are abstract vectors that extract different components of an input word. We have Q, K, and V vectors for every single word. We use these to compute the attention vectors for every word using this kind of formula. For multi-headed attention, we have multiple weight matrices, WQ, WK, and WV, so we will have multiple attention vectors, Z, for every word. However, our neural net is only expecting one attention vector per word. So we use another weighted matrix, WZ, to make sure that the output is still an attention vector per word. Additionally, after every layer, we apply some form of normalization. Typically, we would apply a batch normalization. This smoothens out the loss surface, making it easier to optimize while using larger learning rates. This is the TLDR, but that's what it does. But we can actually use something called layer normalization, making the normalization across each feature instead of each sample. It's better for stabilization.
Now that we have a brief overview in mind, we can now start delving into individual components of the transformer neural network. So let's start with the attention mechanism. This here is a recurrent neural network that's rolled out. And X's are the inputs, the O's are the outputs, the H's are the hidden states, and the Y is the training label. Recurrent neural networks used to be the state-of-the-art for sequence-to-sequence modeling. Sequences can be an ordered set of tokens, which could be like a set of words to form a sentence, for example. And so these recurrent neural networks in many applications of natural language processing were the state-of-the-art for sequence-to-sequence tasks. However, they suffer from two main disadvantages. So the first is that they're slow. We need to feed these inputs one at a time in order to generate the outputs sequentially one at a time. Also, their training algorithm is pretty slow too. We use a truncated version of backpropagation to train them, and the algorithm is called truncated backpropagation through time. But probably a more pressing issue is that these vectors that are generated intermediately for every word, in case of a word language model, we're not sure if they actually truly represent the context of a word itself. After all, the context of a word depends on the words that come before it, as well as the words that come after it. But it's very clear that from a recurrent neural network perspective and architecture, we're only getting the signals from the words that come just before it. Even the bidirectional recurrent neural networks kind of suffer from an issue here because they just look at left to right and right to left context separately and then concatenate them. So there might be some true meaning that's kind of lost when generating these vectors for every word. One way to improve the quality of the vectors generated is via an attention mechanism. So for example, let's say that we have an input sentence that is, my name is Ajay. It's 4 words where each of them can be represented by their own vectors. Using attention, we can decide which parts each word needs to focus on. In this case, there's like a table 4x4 where the bright spots are the spots where this word is focusing on. So for example, my is actually focusing a lot on the word name, and it's going to use the context of name in order to incorporate it in its own feature vector. And the same thing is with Ajay, where Ajay and name are actually quite closely related. And so the vector that corresponds to Ajay is going to incorporate some more context with respect to name, which comes before it. And so, using attention, we can have every word vector better incorporate the context either before it or after it. All of it can be incorporated much better in their vector than the corresponding recurrent neural network counterpart. This form of attention here is self-attention because we are attending on the same sentence as we're using as input. However, attention has many other forms and can also be used in other applications, including like computer vision. The transformer neural network architecture has the attention piece at its crux. Let's actually walk through an example where we're going to translate this English sentence to a Kannada sentence. Kannada is a regional language in India. I am from the state of Karnataka within India where this is spoken, so we're going to just work with that language and you're going to learn some Kannada, so that's going to be fun. We now have the input sentence, my name is Ajay. We pass this simultaneously, all these words, into the encoder of the transformer neural network architecture. This will generate 4 vectors, 1 for each word. Now, technically, the way that's implemented is that these transformer architectures are going to generate word pieces or subwords or byte pair encodings, which are like broken down versions of these words and not full words themselves. But I'm just going to call this a word level language model just for simplicity here. Now that we have these vectors generated, we then pass this simultaneously all into the decoder architecture. And we start with a simple start token. Passing this in, and we now generate the first word. In this case, it needs to generate the Kannada translation of this sentence. And so it'll start by generating the first word, which is nanna. This means my in Kannada. This is now taken as an input into the decoder for the next phase, and it's going to generate the next word, which is hesaru. This means name in Kannada. And then once again, it takes this word as the input in order to generate the next word, which is Ajay. And so transformers can be used to translate from English to any other language like Kannada, and also other sequence-to-sequence tasks. Now, the part of the video that we want to really focus on is this encoder piece. In fact, I'm going to break down this encoder piece further by saying here are the 4 inputs. My name is Ajay. After positional encoding, we're going to get these yellow vectors. And typically, the size of the vectors given in the paper is about 512 dimensions for each. Then these are then passed into our encoder, and the encoder is going to generate another set of vectors. The idea here is that through this attention mechanism, these vectors are going to be much more context aware and hence higher quality than these vectors over here. And specifically, the main crux of the reason is this multi-headed attention part. And so we're going to dive into some code, intuition, and math behind exactly how this works. Now, one thing to note from this transformer architecture is how exactly does this architecture overcome the disadvantages of the recurrent neural networks that I mentioned before. So the first disadvantage I mentioned was slow training because of sequential inputs and sequential outputs. In this case, we can actually process data in parallel, and so we can make use of modern GPUs. And as I mentioned before, in order to make sure that these vectors are of higher quality and more context aware, we have the attention mechanism that's built in. So let's dive further into this attention mechanism. Now, the multi-headed attention part in the transformer architecture kind of looks like this from the main paper, but it's pretty confusing, so I'm going to be breaking this down. Essentially, every single word that is input to our transformer is going to have 3 vectors. We have a query vector, which indicates what am I looking for. We have a key vector, which is going to say what can I offer. And then we have the value vector, which is what I actually offer. Now, jumping into a Colab notebook, we're going to be implementing this all with NumPy. So we have a query vector, a key vector, and a value vector that is randomly initialized. L is going to be the length of the input sequence. In this case, it's my name is Ajay, so I put it as 4. And then the size of each of these vectors, for illustrative purposes, I've put it as being 8. And I have randomly initialized via the normal distribution using the randn function. Doing so, you kind of get these vectors that look like this. So it's for every single word. This could be my, for example. It's going to have an 8 cross 1 vector. For value and for key, it's also going to have another 8 cross 1 vector. And then for q, it's also going to have an 8 cross 1 vector. All of them for the word my. The same is for the name, is, and a j. Next, let's talk about some self-attention. In order to create an initial attention matrix, we need every word to look at every single other word just to see if it has a higher affinity towards it or not. And this is represented by the query, which is for every word, it is what I am looking for, and then a key, which is what I currently have. This product leads to a 4x4 matrix because we had a sequence of 4 words. My name is Ajay. And in each case, it's going to be proportional to exactly how much attention we want to focus on each word. Now, for example, here, this first line is going to be for the my vector and how much it's going to focus on other vectors. In this case, it's going to focus the most on the word name. And similarly, we can see that for other cases. This here is the huge crux of the attention figure that I showed earlier. Now, second is, why do we need this little denominator, the square root of some dimension of q and k? Well, this is because we want to minimize the variance and hence stabilize the values of this q dot k transpose vector. We can actually see that by looking at the variance of the query vector, the key vector, and the multiplication of both of them. And while the query and key vector are close to 1, the variance of the multiplication is much higher. And so in order to make sure that we stabilize these values and reduce its variance, we divide it by the square root of the dimension of the query vector. And so you can see that these values are now much more in the same range. And so if we actually apply the scaling, you'll see that the vector generated will now have values that are also of much lower variance and in the same range. The next step we can talk about is masking. So masking is required specifically in the decoder part of the transformer neural network so that we don't look at a future word when trying to generate the current context of the current word. This is because it would be considered cheating. In reality, in the real world, you don't know the words that are going to be generated next, so you can't really create your vectors based off of those words. However, for the encoder, masking isn't really required because all of our inputs are passed into the transformer simultaneously. Yet, let's actually walk through this process of what's going on. So first I'm creating this triangular matrix with all of the values below the diagonal as 1 and above the diagonal as 0. And this will simulate the fact that I just mentioned where, for example, my, in the sentence my name is Ajay, can only look at itself and nothing else. Name can only look at my and name. Is can only look at my name is, and Ajay can only look at my name is Ajay. Now, I'm actually going to transform this such that I just made every single one a 0 and also every 0 and negative infinity. I did this because if you apply this mask, you'll notice that it's the exact same values for the lower diagonal as it was without the mask over here. But the values that are above that mask are just going to be considered as negative infinity, which means that we're not really going to be getting any context from it. Specifically, y negative infinity and y 0 is also because, well, first I'm adding it here, and second, it's also because of the softmax operation that we're going to be performing next. The softmax operation is used to convert a vector into a probability distribution so that their values add up to 1, and they're also very interpretable and stable. So I've done a little interpretation of exactly the math in this sentence over here. And on applying this math, we kind of get the final attention function over here as this value. Now, I've applied the mask, but let's say hypothetically, if I didn't apply the mask, let's just see how it looks. The numbers look like this, where you'll see every row is going to add up to 1 because it's a probability distribution. But if you apply the mask right now, you'll notice that the attention vector actually doesn't incorporate any word that comes after it because we don't want any context after it. This basically means that the word my is only going to focus on the first word, and the name can only focus on my name, and it's getting the weights as such. My name is going to be can focus on the first 3, and a J can focus on the first 4. This is required for the decoder, but we don't need the mask for the encoder. Now, if we multiply the attention matrix and the value matrix, we actually get these new set of matrices, which should better encapsulate the context of a word. You can compare the before attention with the after attention here. And because this is masked, you'll notice that the first vectors, like my, are going to be almost exactly the same. Whereas as you go to the later words, you'll notice how different these vectors actually become. I've now put all of this logic into a function right here, which takes in the query vector, the key vector, the value vector, and an optional mask. And this hence can be used for both the encoder and the decoder, where in the encoder, we don't really need to pass in this mask, where we're going to have like the new vectors that look like this, and the attention vectors that can actually pay attention to any word. But we can also, for the decoder, go back and pass in the value of mask, such that we make sure that no word is able to get context from the words that come after it. And so we have another type of value matrix that's generated. What we did right now was just for a single attention head. And like that, we can have multiple attention heads and then stack their results on top of each other in order to get multi-headed attention. And according to the paper, this is actually what is being done in the actual production transformer neural network architecture. Now that we have an idea of attention and even how to code it out in Python, let's actually look at multi-headed attention. I'm just going to take an example word vector over here. This could be like one of the words if my name is a J. Let's just say that it's the net vector for name. This is going to be a 512 dimensional vector, which we break down into 3 component vectors. And every word like this is going to have a query vector, which represents what am I looking for, the key vector, which is what I can offer, and the value vector, which is what I actually offer. And each of them are their own 512 cross 1 vectors. Now, in actuality, these vectors are actually each broken up into separate pieces. In this case, it's broken down into 8 pieces, and each piece is going to be a part of creating an attention head. So we have 8 attention heads, so we break each vector down into 8 pieces. And now each of these is then fed into some attention unit, which we will code out very soon, along with all the other words too. This is just a breakdown of the word name, but we also have the my, the name, then is, and a J, and all of them will be broken down in a very similar way, passed to an attention unit, and we're going to generate for each head this attention matrix, which is going to be a sequence by sequence in length if the sentence. In this case, it's a 4 cross 4 because there are 4 words in the sequence. And each of these rows will add up to a 1 because it's a probability distribution. And there will be 8 such attention matrices as we have 8 attention heads in this multi-head attention system. This is then going to generate other output vectors that are concatenated in order to generate a vector that actually has very good contextual awareness. Making this input word vector more contextually aware is actually the goal of this attention unit and this multi-head attention mechanism. Let's now code all of that out. So I'm going to be importing a bunch of libraries, and I'm going to be using PyTorch for this demonstration. I now set a few variables. The sequence length is the length of my input sentence, and typically you would set a maximum sequence length so that all of your vectors are going to be fixed size. In this case, it's going to be 4. That's my name is Ajay. The batch size is going to help in parallel processing. In this case, I'm sending it to 1 for demonstration purposes. We then have input dimension, which is the vector dimension of every word that goes into the attention unit. Then dmodel is the output of the attention unit for every single word. And now this X over here is going to be some randomly sampled input, since I'm not going to be creating the position encoding and the input phase right now. I'm just generating some random data. The input is going to be of batch size cross sequence length cross input dimensions, which is 1 cross 4 cross 512. Note that this x value is not the value over here, but it's the value that's input at this point just before we get into the multi-head attention phase. Now we're going to be mapping the input from this dimension of 512 to 3 times the model dimension, which is again 3 times 512. And this is done to create the query vector, the key vector, and the value vector all concatenated, and all of them have all the 8 attention heads, which we will split up later. We then pass the input to this layer to generate the QKV vector, and this is its dimension. It's one batch, 4 words, and each word vector is 1536 in size. Now, I wanted to get an idea of what are the kind of values that we see here, and since I'm sampling from a random normal distribution, you'll see the values that look like this. But this distribution of all the values in this entire tensor is going to be very different depending on how we generate the data, depending on the positional encodings and the inputs. Now we have 8 attention heads that we're considering, and each is going to be 512 divided by 8, which is going to be 64. And so we will now reshape our QKV matrix to break down the last dimension into a product of the number of heads, and of course 3 times the head dimension. And this 3, just as a reminder, exists because it's a combination of the query vector, the key vector, and the value vector. And so we get a tensor that looks like this in shape. Now I'm going to be switching around just the second and the third dimensions so that the head is over here and then the number of sequences is over here, so it's easier to perform parallel operations on these last 2 dimensions. Now we obtain the query key and value vectors individually by basically breaking down this entire tensor by its last dimension, and hence the input is -1. And so this 192 breaks down into 3 components of 64 dimensions each, and this is where you see the query key and value vectors broken down, as I mentioned before. Now we're actually going to perform the attention mechanism. A lot of this process is kind of what I mentioned in the last video, so you can look at more details there if you want to get a much deeper explanation, but I'll still go through some parts of it since I'm doing it in PyTorch here, and there I did it in NumPy. So first of all, we're going to get the size of one of these vectors, which is dk. This should be 64 in our case. Now every word has a query vector, and it's going to compare its query vector to every other word's key vector, and that's represented by this matrix multiplication over here. And we can represent that by this code. Now notice that you have to use the transpose function, and you can't just do like a .t to typically transpose, because these are tensors that are 4-dimensional and not simply just 2-dimensional matrices. And so we specify the transpose along with the dimensions along which we want to transpose. In this case, we wanted to transpose the last 2 dimensions, which are the sequence length, as well as the dimension size, or the head dimension size for every one of these words in every head. And so the last 2 dimensions of the query vector are like 4 cross 64. This will be a 64 cross 4. And so we'll end with up with a 4 cross 4 matrix, which is basically the sequence length by the sequence length. We're scaling here in order to make sure that the variance of these values is much smaller, so that these values just don't go out of control, especially since this is a trainable machine learning model. This here is just a dummy example just to show how important transpose is, and also that it takes in these 2 values of which dimensions along which you want to transpose your tensor. And it doesn't matter about the ordering, as long as the same dimensions are present, it'll yield the same result. Now let's talk about masking. So we notice here that in the encoder, we don't really require any kind of masking, whereas in the decoder, we require masking for self-attention. And this is done to ensure that the decoder does not cheat. The goal of the attention mechanism is to gain context from words that are around it. During the encoding phase, we actually have all words which are passed in parallel simultaneously, so we can generate vectors by taking the context of words that come before it as well as words that come after. In the decoder, however, we generate words one at a time. So when generating context, we only want to look at words that come before it, because we don't even have the words that come after it. Coming back to the code, we're basically going to have our scaled tensor, which is our 1 cross 8 cross 4 cross 4 tensor that we generated just previously. And we're going to fill this up with negative infinity values. And then we're going to basically take this mask, and this is like an upper triangular mask where we leave the upper values above the diagonal the same as they are, and I'll fill the lower diagonal with just zeros. This diagonal argument is just to say how many positions above or below the diagonal we want to actually fill with those zeros. And so if we just print out the mask for a single head, it'll look like this. And note that it's the same exact dimensions as our scaled tensor. So we can add them both together and we'll get, well, this is the tensor for one head, which will be a 4x4 matrix. It's going to look like this, where we have lower diagonal elements, the exact same as what scaled would have been because we're just adding 0, and the upper diagonal elements would be whatever the negative infinity is. Now we're doing negative infinity over here specifically because we're going to be doing a softmax operation, which takes like exponents. And so the exponents of 0 will become 1, the exponents of negative infinity will become 0, so that you cannot cheat and look forward. And so we can apply that softmax here because these tensor values are all over the place. And when you actually apply the tensor values, you'll see that the sum of each of these records will become 1. And in this case, I just tried to do it for this example where we're taking e to the power of this first term divided by the sum of e to the power of all of these terms, which I've taken here. And you'll see it's like 0.6269. And on applying the actual attention, now we apply attention though using the softmax built-in function. We'll apply it to our new scaled tensor. And the dimension we apply it to is the last dimension. We want to just apply to this last dimension, which incorporates this row itself, row by row. We now take this value vector, which is, remember, this is what is actually being offered by every single word, in order to generate the new value vectors. And the idea here is that these new value vectors are going to be much more context aware than the original value vectors and the original input vectors. And so we'll end up with, for every batch, for every head, for every word in the sequence, we'll have a 64-dimensional vector. Now, I've created a function that does exactly everything that I just described, and I also added in an optional mask function, depending on whether we're dealing with the encoder or the decoder. So for example, if I just execute this, you'll see that we have an attention vector that kind of looks like this. But let's say that we actually pass in the mask that we just created. In this case, you'll see that the size is the exact same, but the attention vector is now going to be masked for the decoder. So whatever I have the encoder, this is good for the decoder. And then we can now have all of the value vectors for every single attention head for every single word, which are 64-dimensional vectors. And then what we do now is we are going to now combine or concatenate all of those heads together. For 8 heads, we're going to now make them 512-dimensional vectors, which is exactly the input dimension. And then so that these heads can also communicate with each other, the information that they've learned, we are just going to pass it through a linear layer, which is just a feed-forward layer, 512 cross 512, and this doesn't change the dimension. And so this output vector is now going to be much more context-aware than the input vector was. Now, all of this code entirely I've combined together as well by creating, well, this is the same function I wrote before, but I've also written a class called multi-headed attention, which is going to now take in a constructor, which will initialize some of these parameters that I talked about along the video, as well as a forward path. So when you execute a forward pass of our multi-head attention, it's going to execute the same exact lines of code that we just talked about. Now, I kind of executed this for some random inputs where the input dimension was much larger, and the batch size was also something that's more reasonable. I just put it as 30 instead of just 1, and I execute the forward pass of this multi-head attention, and you'll see the same kind of results where the input batch 30, we have like 5 words in the sentence, and it's going to generate vectors of, let's say each of them is 1024. Then the query key and value vectors of all heads are combined to generate a 1536 dimensional vector. This is then broken down into 8 attention heads. We swap these to the attention heads as well as the number of send words in the sequence. And then we break this down into query key and value tensors in our case, and each of them will be like 64-dimensional vectors for every word. We then have the attention value matrices for every single attention head, which we eventually concatenate, and then we also help them communicate with each other. Alright, so now that we've taken a look at multi-headed attention and its code, let's now shift gears towards positional encoding. So let's actually walk through exactly how the initial part of the transformer neural network architecture works so that it kind of motivates positional encodings better. So first we have the sentence that we want to input in English that is, my name is Ajay. Now, typically, the way that transformers and all these machine learning models work is that they understand numbers, they understand vectors, but they don't understand exactly, English words. And so what we would do is, in order to make sure that we always pass in a fixed length matrix, we would pad the rest of all the words that are not present or not, with just like a dummy character or dummy sequence input. And this would just be the maximum number of words that is allowed into the transformer. Each of these words is then just one hot encoded. Vocab size is the number of words in our dictionary. That is the number of possible words that can be used as an input. We now pass this into a feed-forward layer where each of these vectors is going to be mapped to a 512 dimensional vector. And the parameters here are learnable via backpropagation. And the number of parameters would be the vocabulary size times 512 parameters to learn. Now the output of this would just be a set of 512 dimensional vectors, one for each input in the sequence. And it's to this that we're going to add some positional encoding, which is of the same size. And on doing so, we're now going to get another set of word vectors of the same 512 dimensions. Now for each word vector, we want to generate a query, a key, and a value vector, all of 512 dimensions each. And so we would pass each vector into, well, this query, key, and value set of weights, which will map one input vector to the output either query vector. This will map it to the key vector, and this will map it to the value vector. And we do this for every single word. And so the number of total vectors here would be 3 times the maximum sequence length, because it's 3 for every word. Note here that these green transformations are basically like learnable parameters. In this case, it would be 512 times 512 learnable parameters for each of these. Now it's from this point that we could probably split each of these vectors into multiple heads and perform multi-headed attention. But I think I've explained some of this concept in another video called Multi-Head Attention for Transformers, so please do check that out for more information there. However, for now, I kind of want to just focus more on this positional encoding, and I hope that this flow overall kind of just illustrates exactly where positional encoding fits in and how it fits in. So this is the formulation for computing positional encoding in the transformer. Now, this is actually just to compute it for every single element of this matrix that we mentioned before. In this case, we have pos, which is the position of the word in the sequence. I is the index of the dimension, and D model is the dimension length, which we have taken to be 512. So a big question here is, why exactly did we formulate positional embedding in this way? The first reason is periodicity. Sine and cosine functions are periodic functions, so they will repeat after some point of time. What this means is that, let's say that we want to look at this positional encoding, and we're looking at it for this specific word, that is the third word. Let's say that at some point we're going to compute the attention matrix and try to determine how much attention this word should pay to all other words. Now during this phase, because of periodicity, this word is going to be able to pay attention to, let's say, 5 words after it, and then 10 words after it, and then 15 words after it in a much more tractable way. Now the second reason is constrained values. Sine and cosine will constrain the values to be between +1 and -1. But without that, these values, at least in the positive direction, are not bounded. And so what this would mean is that, like, positional encoding for this vector might be smaller than this next vector, which will be smaller than this next vector, and so on. And during the time that we compute the actual attention matrices, you'll notice that the vector here is not going to be able to attend to vectors that are very far away from it, and so it will not be able to derive any context from them. The last reason is that it's easy to extrapolate for long sequences. So this here is just going to be a very deterministic formula that's very easy to compute. And even if we haven't seen certain sequence lengths in our training set, we'll always be able to interpret them in our test set. And so because of easy extrapolation, it's used. Now that we got that theory out of the way, let's walk through some PyTorch code to create some positional encodings. So we'll start by importing torch, and then we define a max sequence length. This is the maximum number of words that can be passed into our transformer simultaneously. So in my case, the sequence length was 4 because it was my name is a J, but I'm defining the max length as 10. In reality, this would be in the thousands. dmodel is going to be the dimension of the embeddings. It's typically 512, but for illustrative purposes, I just use 6. Now, this top 2 is exactly the same formulation that I used to show positional encodings, but honestly, I'm going to rewrite it as just these 2 formulations so that it becomes easier to see and also easier to program. But they remain the same thing. Let's now start by coding out this denominator for when I is even. So for this, I would just use a range just to get a set of values between 0 and dmodel. That's 0 to 6, skipping 2. So that's 0, 2, and 4. And so we can now compute the denominator over here by taking 10 to the power of all of these values that we get divided by dmodel. And that's exactly what I do here. That's 10,000 to the power of everything that we just received here, divided by dmodel. And so we get a set of values here. We now do the same thing for the odd dimensions. So we compute the odd dimensions, where it's from 1 to 6, skipping 2. And so we get 1, 3, and 5. And then performing the same operation right here, performing the same operation, we get these numbers. Now what you'll notice here is that the vectors that we got for the even denominator, that is for this, and the vector that we got for this denominator are exactly the same. And this kind of makes sense. You'll notice that the odd indices are 1 more than the even indices. And in the formulation, we always subtract 1 from the odd indices. So they effectively just became the same thing. And so instead of using an odd denominator and even denominator, I just am going to use one called denominator, and that'll be used for both cases. Now let's just determine every single position for the sequence. So we can define every position by just taking all the values from 1 to 10, and then we'll reshape it to be a 2-dimensional matrix with the second dimension as 1, and you'll get this 2-dimensional matrix here, 1 for every word. Now we want to divide every position with the denominator value that we computed earlier. And for even cases, we're going to take sine, and for odd instances, we're going to take the cosine. And so this is going to lead to 2 10 cross 3-dimensional vectors. So this is for even positions, and then we have the same exact thing for odd positions. Now what we want though is to interleave these 2 matrices. So for example, for the even position, we want this to be the first index, and then we want this to be the second index, and then the third index, and then the fourth index, but starting at 0. So it'll be the 0th index, first index, second index, third index, and so on. And in order to do that, I basically stack them together on the second dimension so that the 2 that we need to stack on top of each other are right next to each other. This will give us a 10 cross 3 cross 2 tensor, and we just flatten it. And effectively, we're going to be getting that interleavement here too. And so for our first word, this will be the positional encoding. For the second word, it's this one. For the third word, it's here, and so on. Now I've put together everything that we just talked about into this little cute class here so that it's reusable, and it has the exact same instances of everything that we just discussed. And we can now just make some calls to the positional encoding, passing the elements into the constructor, and then we just generate the forward pass, which will give us the exact same positional encoding matrix. All right, so that was positional encoding and its code. Now that we have a good idea of that, let's now shift gears to layer normalization. I kind of want to focus on these add and norm parts over here. What are we adding and normalizing? So in order to understand that, let's actually blow this encoder up. What we get is this not so complicated architecture that I've drawn by hand, but we'll actually just pick apart what's important here. We have the input my name is Ajay, and let's say we want to translate this from English to French. We first pad this up with word tokens. Each word is then represented by some one-hot encoded vector. Now, technically, it would not be the words that are represented like this, but typically word pieces called byte pair encodings. But for the sake of simplicity right now, I'm just considering them as one-hot word vectors. Because each of these are one-hot vectors, they're going to be the same size as the vocabulary itself. That is, all possible words that can possibly occur. We then transform these one-hot word vectors into 512-dimensional word vectors. Because all the words are passed in parallel, there is no sense of ordering, but English sentences have words that are ordered specifically, and so we pass in some positional encoding to encode orders. We then add the input to the positional encoding in order to get these positionally encoded vectors. Now it's from here that the multi-head attention unit is kicked off, where each vector is now split up into 3 vectors of query, key, and value. Each of these are 512-dimensional vectors. And so we're going to end up with 3 times the maximum sequence length, because it's basically 3 times the number of words that we saw here. We now split each of these query, key, and value vectors into 8 parts, and each part is going to be a vector for 1 head, and there are 8 heads according to the main paper. And each of these heads are then now passed into 8 attention blocks. And each of these attention blocks are basically going to just multiply the query and key vectors, and then apply some scaling as well as masking. Now, once we pass it through the attention unit, we will get attention matrices, which is going to be sequence length cross sequence length. That's the number of words cross the number of words, in order to see exactly how much attention each word should pay to the other. We then multiply it by every head's value matrix, which is essentially going to be the sequence length cross 64. And so when we multiply these matrices together, we're going to get 8 individual vectors, which are going to be the maximum sequence length cross 64 each. And then we just concatenate them. Since there's 8, it'll be maximum sequence length cross 64 times 8, which is 512. Now, if we compare this to the original transformer image, this matrix is essentially going to be the output right at this stage, just before the normalization. However, you'll notice that, while this added norm actually takes the input of this matrix, which is like right here, you can see there's a connection, but it also has this residual connection over here, where it not only takes this matrix, but also the matrix after the positional encoding. Now, these residual connections are actually done to ensure that there is a stronger information signal that flows through deep networks. And this is required because during backpropagation, you'll notice that there will be vanishing gradients, which means that there's eventually a case where as you keep backpropagating, the gradient updates become 0 and this model stops learning. So to prevent that, we kind of induce more stronger signals from the input in different parts of the network. And so coming back to our figure, you'll see that we will add this out matrix along with X dash. And if you recall, this X dash is exactly what we saw before, where it is the output of adding the input with your positional encoding. That is this matrix. And hence, you can see that we are adding 2 matrices and then normalizing. Add and norm. So now that you know why we add and norm, let's actually get into the details of layer normalization itself. What and why layer normalization? Now, to understand layer normalization, we break it apart into 2 parts, which is normalization, and then by layers. Normalization, what and why? Typically, these activations of these neurons will be a wide range of positive and negative values. Normalization encapsulates these values within a much smaller range and typically centered around 0. What this allows for is much more stable training, as during the backpropagation phase and when we actually perform a gradient step, we are taking much more even steps, so it is now easier to learn. And hence, it is faster and also more stable training to get to the optimal position or these optimal parameter values more consistently and in a quick way. Now, layer normalization is the strategy in which we apply normalization to a neural network. In this case, we are going to ensure that the activation values of every neuron in every layer is normalized such that all the activation values in a layer will have like a center like 0 and maybe like a standard deviation of 1. To understand a little more detail, let's say that X, Y, Z, and O are the activation vectors for every single one of these layers that we have here. Now, in typical neural network fashion, we would have some activation and apply it to the weights times that vector and add some bias. This is without any kind of normalization. But now to add this normalization, we'll take exactly whatever the result is here. We will subtract the mean of the activation values of this layer, divided by the standard deviation of the activation values of this layer, and we are going to ensure that we have like learnable parameters, gamma and beta. This is the same, gamma 1 and beta 1 is the same for this entire layer, and gamma 2 and beta 2 are for this layer. Now, gamma 1 and beta 1 and also gamma 2 and beta 2 are learnable parameters. So as we keep getting more and more inputs to this network over time, and we perform like a backpropagation step, these values are going to be learned and changed in order to optimize the objective of the loss function. Now let's actually go into more details by working out an example. Let's say that we have two input vectors. In this case, I've represented it as a matrix. So in this case, you can say it's like 2 words, and each word is like represented by 3 dimensions. And let's say that we want to perform some normalization, specifically layer normalization for this matrix. And to do this, we compute mean and standard deviation across the layer. And so the first mu11, which will be the first part of the mean matrix, it's going to be just the mean of all of the embedding values here, and you'll get 0.2. Similarly, the mean of all of these values over here, you get 0.233. And now we can use these mu values in order to compute the standard deviation. So we'll take the square root of the mean of the difference of squares between every individual value of the embedding minus the mean for that embedding. So in the first case, it was like 0.2 was the mean, hence I'm writing it here. And each of these individual values, 0.2, 0.1, 0.3, which were the actual embedding values. Doing the math, we're going to get 0.08164 as the result. Similarly, for the next input word, we have the input 0.5, 0.1, 0.1, and we'll subtract the mean for that specific embedding. We'll square it, sum it, take an average, and then square root. And we'll get 0.1855. And so we have the matrices for the mean and also the standard deviation. Now what we can do is subtract the mean and divide by standard deviation. Doing that math, we'll get this matrix over here. And the output completely is going to be the learnable parameter gamma multiplied by every single element in this Y matrix plus beta. Now, what you'll notice, at least initially, if gamma is set to 1 and beta is set to 0, the out will be the same as Y. And you'll notice that for every single one of these layers, you'll see that the mean is 0 and standard deviation is close to 1. Same with this. Mean is 0, standard deviation close to 1. And so these values are just more tractable, and it becomes much more stable during training. Now that we worked through an example, let's actually code layer normalization out. Now, you'll notice here that I've added a batch dimension to the same exact input that we have. This is because during training, we typically would have a batch dimension so that it helps parallelize training, and training just becomes faster. And so we would reshape the input to be the number of words, which is 2. In this case, I've taken the batch size as 1, and we're going to see the embedding for each batch as just 3. Because now we have like this batch dimension, we're also going to use layer normalization not only just for the last layer, but that last layer across some batches. In this case, it's going to be 1, so it's not going to make too much of a difference, but layer normalization is essentially going to be computed across the layer and also the batch, just for your reference. So in this case, that's kind of why we see 1 by 3 dimensional matrices. Otherwise, we would have just seen just 3-dimensional vectors for gamma and beta. And we're going to initialize gamma to be the standard deviation, which is just 1s, whereas betas are just going to be a bunch of 0s. Now I'm basically computing the dimensions for which we want to compute layer normalization. That is the batch dimension as well as the embedding dimension, and it's the last 2 layers. And now we'll just take the mean across the batch dimension and the layer dimension, and we're going to end up with a 2 cross 1 cross 1 tensor. And specifically, we get the same values as before. We have 0.2, 0.233. We do the same kind of computation like we did before for computing the standard deviation. Now you'll notice that we're adding some small epsilon value to this variance, and this is done to ensure, because standard deviation is going to be a denominator over here, it doesn't become 0. And so when we actually do the inputs minus the mean divided by standard deviation, we will get the same exact matrix that we kind of worked out by hand, which is great. And now we're going to multiply gamma, that is a matrix of 1s, to all the values of y, and add zeros. You're kind of still going to get the same exact matrix, but this time you'll notice this additional parameter over here, which means that it has learnable parameters, in this case gamma and beta, which are going to be updating during the actual backpropagation phase. Now, everything that I've just discussed is going to be in this little class called layer normalization, where we have a constructor that takes parameters shape. This is the dimensions along which we actually want to perform layer normalization. It could be just the last one, like we worked out by hand, or the last two that we just saw in the execution above, or even more if we wanted to. It's just a generalized function. Now you can kind of execute this code by just initializing some inputs where we see some 5 cross 3 cross 8 tensors, and then we'll perform some layer normalization here. We can, like I said before, we can either perform layer normalization for the last two or just the last dimension itself, and you'll notice that we just get different values for each case. Now, with this explanation of layer normalization, we've kind of explained a lot of these core components. And what I want to do now is take this architecture and blow it up and explain each and every single component in one detailed swoop. And to do that, I have everything here that's going to be a part of the series is on GitHub, and I've drawn out this entire architecture. And so now we'll be walking through the encoder and the decoder part of the transformer with all of these wonderful details. On reading the Attention is All You Need paper, which introduced the transformer architecture, it doesn't seem like it was written with the intent to be the foundation of BERT, GPT, or language models moving forward. It kind of reads like a paper that less focuses on the architecture and more on accomplishing the specific task of language translation. And so we're going to also blow up and explain the same architecture using language translation from a language called English, which I'm assuming we all know, I guess. Maybe no judgment if you don't. And then to a language called Kannada, which I'm assuming you don't know because it's a very small South Indian language spoken in a very specific state, in a very specific country in the world. But I'm from that region, so I thought I would just create a translator to do so. Let's now talk about the high level of the transformer architecture. The transformer architecture consists of two parts, an encoder and a decoder. During training, the encoder will take the English words of the sentence simultaneously, and it will generate word vectors simultaneously. These word vectors are going to be eventually context aware, as we will continue to train the transformer. And this is because of the attention mechanism, which we'll get to shortly. To the decoder, we're going to take care of our Kannada words simultaneously, but we'll also pass in a start token to indicate the start of the sentence and the end token to indicate the end of a sentence. We will also pass in the English vectors that were generated from the encoder. For the labeled output of the decoder, we shift the translation to the left. This is because, given the start token, we want to predict the first word of the sentence. Given the start token and the first word of the sentence, we want to predict the second word of the sentence. And in case you don't know where this is going, if we're given the start token and the first two words of the sentence, we want to predict the third word, and so on. To determine the model's loss, we compared the prediction made with the softmax and the labeled sentence here. A common loss function used for this kind of problem is the cross-entropy loss. We would compute the cross-entropy loss for every predicted word, add this up to get a single loss. This loss is then backpropagated through the network to update the network's parameters. Now, during inference, let's say that we want to translate the English sentence, "How are you?" to Kannada. We don't have any contextual words, But we do have the English words. So we can generate the English word vectors from the encoder, but we only pass the start token of the Kannada translation to the input of the decoder. This will produce the first word in Kannada translation, which is Neevu. That's how you read this. We then take the start token and Neevu to generate the next word of the sentence, which is Hegidiri. We now pass in all of these words generated and continue generating words until we hit the end token, and this will complete the translation. Now that we took a look at how training and translation inference happen at a very high level, let's blow this architecture up and look at some details. Before starting this out, let's lay out some hyperparameters that we're going to be using through the conversation. So we're translating from English to Kannada. We'll assume that the batch size is 30. The batch size means that we are passing in 30 sentences at once through the network in order to update the weights of the entire network once. And we have the maximum number of words that a sentence can possibly have is 50. And this applies to both languages to keep it simple and consistent when we're seeing in the diagram. I mentioned we have a batch size of 30, but why are we batching? This is for faster training. When training neural networks with gradient descent, we pass a single input, generate an output prediction, compare the prediction and the label, and quantify this as a loss. This loss is backpropagated to update the parameters of the network. And so for every training example passed into the network, the parameters are updated. This is fine for small networks since the updates are quick enough, but for networks like ours, which have like millions of parameters, the updates can be pretty slow. So instead of updating the weights after every single sentence, we will update the weights after seeing a batch of sentence examples. And hence, mini batch gradient descent is of common practice. And in our specific example, we are passing in 30 sentences at a time through the network before any update to our model weights happens. Now, why are we choosing 50 though for the maximum number of words in a sentence? This is so we have a consistent shape of tensors that pass through the model at any given time. There are many implementations too that dynamically size the input, but we'll stick with the same sequence length for every single sentence implementation for this video. Now let's come back to the encoder. So this is the start of the encoder where we have every single word over here. However, computers do not understand words, they understand vectors and numbers. And so we'll be converting each of these words into an embedding. Specifically, embeddings are vectors, and they are like 512 dimensional vectors in our case. So this cube structure over here is essentially a huge tensor that is going to be 30 cross 50 cross 512. That's 30 for this batch dimension, 50 for the number of words in the sentence, cross 512 for each single word representation. We then add a positional encoding of the same shape. These positional encodings are generated from sine and cosine functions, and so they consist of numbers between -1 and +1. They exist because the encoder takes in words simultaneously, but the ordering of these words actually matters. We have the first word followed by the second word, followed by the third word, and so on. This ordering, or positional encoding, is defined by a positional encoder. In the main paper, they are not learnable parameters, but they can be configured to be learnable parameters if need be. There is no evidence at the time of making this video to suggest that using learnable parameters is better than just using the sine and cosine functions to generate positional embeddings. I have more information on this in another video on positional encodings with code. We then get this final tensor over here that we pass through a feed-forward network in order to get query vectors, key vectors, and value vectors. So every word is split up into 3 vectors: a query vector, a key vector, and a value vector. In past videos on this topic, I have discussed a very specific differences between them, but this is honestly just for our understanding, and the difference isn't very explicit to the model itself. I've received a number of comments that dig a little too deep into the exact definitions of these 3 query, key, and value vectors, and we could construct some difference between them, but in practice they could quite literally be the exact same vectors for the encoder case. And this is best represented with the encoder architecture, as the query key and values are merely the result of a feed-forward transformation, and they're really nothing special. Now, what makes the query key and value vectors different are the operations that we will eventually perform on them. Since every word is represented by 3 vectors, so we have every 512 dimensional vector converted into a 512 dimensions times 3, which is 1,536. So every single one of these 1,536 dimensional vectors now constitutes a word. And the reason we break this up is to perform the multi-head attention. Zooming out a little bit over here, you'll see that there's this huge white stacked block. So there's going to be 8 of these stacked blocks on top of each other, and I do that for 8 heads in this multi-head attention. This is masked multi-head self-attention. It is self-attention because we're trying to analyze the context and build context within the same sentence. So every word in the sentence is compared to every word in the same sentence, hence self-attention. It's multi-head because we have 8 of these layers. And then it's masked because we're going to be discussing the padding mask over here, since there are many sentences that are not 50 words in length, and so we would be adding padding tokens. But these padding tokens should not be considered when computing a loss and also performing backpropagation. And so we want to effectively mask these out. The logic you see in this one grid is just for one attention head. And like this, you can imagine that there are 8 parallel processes going on. So this 1,536 dimensional word vector for every single word is going to be broken up into 8 pieces. So we have this query part, which is going to be broken up into 8 pieces, the key part broken up into 8 pieces, and the value part broken up into 8 pieces. Each piece is essentially going to be a 64 dimensional vector if you do the math. So that's 64 dimension of the query, 64 dimension of the key, 64 dimension of the value, and we stack them kind of in this way to get 64 times 3, which is a 192 dimensional vector representing every word for one head. What we do is take the query vector and the key vectors, and we will multiply them, and using these shapes, of course, that's 30 cross 50 cross 64, and 30 cross 64 cross 50. And if you do a matrix multiplication, this will be a 30 cross 50 cross 50. Specifically, we're doing the multiplication along these last 2 dimensions and not the batch dimension. The fact that we're comparing every word in the English sentence, which is the query vector, with every word in the same English sentence, which is the key vector, makes this a self-attention. This is the semblance of a first attention matrix, and typically after this, even before we add the padding mask, we might even do some sort of scaling so that we prevent all of these values here from the multiplication from exploding too much to high numbers or very low numbers, and thus also stabilize the training. Scaling simply means dividing every value in our self-attention tensor by a constant value, and the value that is used in the main paper is the square root of the key dimension size vector for one head. And since our key is 64 dimensions for one head, we would typically divide each value by 8 to scale. This will ensure the activation values are neither too large nor too small. But once we do that scaling too, we're going to add a padding mask. A padding mask will prevent the padding tokens from propagating values. Technically, they should be 0 for pass-through and negative infinity for masking. This is because we will eventually perform a softmax. The softmax operation uses exponents. So the exponent of 0 becomes 1, which is a pass-through, and the exponent of negative infinity becomes 0, which will mask or will block information from passing through. In practice, the way that we would accomplish this is for every single padding value, we would introduce a very low negative number, kind of like negative 10 to the power of 9. It can't be negative infinity because a future softmax operation might fail, because if every single row is going to be a negative infinity and we apply a softmax, you'll get 0 by 0, which leads to numerical instability. and hence what we would do instead is apply a very low negative number so that there's going to be at least some form of pass-through that occurs even after doing all the math. But this pass-through is so negligible that it shouldn't really affect your training too much. So once we apply the padding mask, we will now apply a softmax activation, and then we will actually have an attention matrix. And in this attention matrix, you'll see that it's 30 cross number of words cross number of words, number of words cross number of words. And so you'll see like a probability distribution for every single row over here. And so each value in this matrix is going to quantify how much attention each word should pay to every other word. We then apply the value matrix that we computed way back in the beginning over here in order to get a 30 cross 50 cross 64 dimensional value tensors. And these value tensors will be very contextually aware. And this is the output of just one attention head. But recall that we have 8 of these attention heads. And so if we concatenate them one after the other, we're going to get 64 times 8 of these, which is 512. And so this concatenated tensor is now a very much so contextually aware tensor, at least compared to the input to this entire multi-head attention unit. You'll see here now that we're adding a residual tensor. When performing backpropagation, the loss value propagates in the backward direction to change the weights. You'll notice the largest changes happen towards the end of the network since it's closest to the loss signal. But as propagation goes on in the backward direction, the change in parameters will continue to get smaller. This is okay for shallower networks, but as networks get very deep, we might run into situations where the loss might not be able to propagate to all parts of the network. And so the parameters don't change as the gradients vanish and no learning happens. Skip connections or residual connections help by enabling better propagation of the inputs in the forward direction and the loss in the backward direction. We see this a lot in research involving deep convolutional neural networks, and they're used here too. So once we add a residual tensor, we'll now get this new tensor that hopefully will carry out the activations and the weights and also make sure that these weights update. We then perform layer normalization. The goal of normalization is to ensure stable training, so activations during the forward phase and the gradient updates during the backpropagation phase are not too large in magnitude. Mathematically, normalization would involve subtracting the values with a mean and dividing by a standard deviation. In batch normalization, we normalize the values across the batch, that is the 30 dimension. But in layer normalization, we normalize the values across the feature layer, that is the 512 dimension. And so, for layer normalization, we subtract each value of the tensor with the layer mean and divide it by the layer standard deviation. Now, in practice, we add a very small epsilon term to the standard deviation, which is of the order 10 to the negative 5, in order to prevent a 0 divided by 0 case from occurring. Additionally, we also optionally use learnable parameters called gamma and beta to track changes across different training examples. I've explained the process with more details with examples and code in a video on just layer normalization too. We now take the output tensor, pass it through a feed-forward layer, and then pass it back through a feed-forward layer just to capture some more information. And then we'll perform the same addition of the residual tensor and layer normalization in order to finally get a set of, for every single word, we will have 512 dimensional tensors, and each of these tensors is going to be very well contextually aware. And this here is the output of the entire encoder architecture. Now, once we have very contextually aware items here, we're going to pass it through a feed-forward network, but I'll explain exactly what and why we have key and value vectors here. But before I do this, let's go back to the decoder architecture and explore the beginning of it. So with the decoder, we want to generate the output translation. And for this, we will pass in the input sentences with a start token, followed by the sentence values, followed by the end token, and then a bunch of padding tokens until we hit 50 words. Now, in much the same way as before, we add a positional encoding. And once we add a positional encoding, we're going to pass it through a feed-forward network to get query key and value vectors and perform mass self-attention as we did in the English case. So it's mass multi-head self-attention here. So it's the same dimensions. We'll take the query key value, split it up into 8 different heads, multiply the query and the key tensor. We have an attention matrix essentially over here, which we will typically scale before adding a mask. However, in this case, we not only need to add a padding mask, but we also need to add a look ahead mask. So a look ahead mask will ensure that the decoder is not cheating, because during the generation phase, that is the inference phase when you want to actually just start translating sentences, we don't have access to future Kannada words, the future destination target language words. And so during training, we need to apply a mask to ensure that it does not look ahead of its current self. So that means that the third word in the sentence cannot look at the fourth word in order to see what it can attend to. And so it cannot derive any contextual information from that during the training phase. And so we will add the look ahead mask along with the padding mask. We then apply softmax to actually get attention values and probability distribution like values for every single word, how much it needs to pay attention to every other word in that sentence. And then multiplying it with this value matrix, we'll get some value tensors, which we concatenate across all of the 8 batches over here in order to get the final concatenated tensor. We'll then add a residual tensor so that we can ensure that information is going to propagate. We apply layer normalization, and now we are going to get this batch over here, which I'll just call it directly as Q. This is going to be a set of query vectors that we're going to be inputting to our mass multi-head cross attention layer now. So in order to perform cross attention, this is going to be, instead of like every word in the sentence to every word in the same sentence, it'll be every word in this target sentence Kannada to every source word in the English sentence. And so the query represents essentially what am I looking for, and that's kind of what we would want to output. That's why this will be the query. The Kannada words will be the query tensors. And now if you can see that there's an arrow that's coming in, but it's coming in from the encoder piece, which is providing, well, we saw these concatenated tensors that are very high quality. We're just going to put a feed-forward network of 512. It'll map 512 dimensions to 1024 dimensions. And so every one of these is for every word will be 512 and 512 for the key and value tensors. This will add English information that we have encoded into the Kannada vectors so that when we're generating the Kannada vectors, we generate an appropriate Kannada translation based on what the English translation has to say, or the English sentence has to say. So we have the query from the Kannada sentence, and then we have the key and value vectors from the English sentence, and then we perform multi-head cross attention, which kind of looks like the other self-attention case, but clearly the source of the query is different, and the key and values are different as well. So we'll multiply the query and key, get an attention matrix, which we will scale, as I mentioned before, to help numerical stability. In this case, we only need a padding mask. This is because every single Kannada word is allowed to see the entire English word sentence. Because we are, during translation phase, we have everything in the encoder. We have all of the English words already, since we need to translate it. And so we just need to add a padding mask, just to zero out any padding information from excess tokens. We'll then perform a softmax to get a probability distribution values of how much attention should each Kannada word pay to an English context. And then we'll eventually get the similar value tensors, which we concatenate across the 8 heads. And this will lead to a 512 dimensional vector for every single Kannada word. And in this case, every Kannada word will have some English context now embedded in it as information. We'll add a residual tensor to ensure that we have extra propagated information throughout the network, because it's a very deep network. And then after performing some layer normalization for stabilizing the values and gradients and a feed-forward layer, we will end up with a 512 dimensional vector that is very context-aware. This entire decoder layer and also the encoder layer can be repeated. I put like a times n up here and also a times n over here. So essentially, after getting these tensors, we can actually create this entire architecture. It'll basically, the control will basically pass back here. And it has the same tensor shape. So we can basically perform this decoding phase again and again as many times as we need. Typically, it's done like a few times. Even once is fine, but it depends on your problem, depends on how many patterns are required to actually understand this translation. But essentially, once you have your final vectors, that is your final Kannada vectors that have English context embedded with them, you can take it into a feed-forward layer in order to expand it to the Kannada vocabulary size. Note the Kannada vocabulary is the number of possible words that our model can see and predict. In this architecture, we made it predict words. So the dictionary might be large and of the order of tens of thousands. However, the sentence sizes are small. You'll see the English sentence, "How are you?" is just size 3, and the Kannada translation for this is just of size 2. And many implementations use character tokenizations or even byte pair encodings to get a good balance of vocabulary size and maximum sequence length. So in this case, for every single batch, for every single word, we are going to have a vector that is the size of the Kannada dictionary. And this is so that we can make it interpretable to us humans. So once we apply a softmax on it, we'll get a probability distribution across all Kannada words, and we can just take the most probable word that it's supposed to be as like the prediction. And this is going to be compared to the labels. This here is the label, which is what it should be, what every single line. So the first line should be encoded as this first word, which is nivu. And the second line over here should be encoded as the second word, which is called hegidiri. And this third line should be encoded as the end token to represent the end of sentence. And it's based on these 3 tokens, the first 3 ones, that we'll be computing a cross-entropy loss, and then we'll be back propagating throughout the network. And when I say throughout the network, we're basically going to be back propagating through the encoder and decoder as well, because the encoder also has a connection over here. So all of the weights of the entire network will be updated once it sees one batch of 30 sentences. And so that's the entire transformer neural network architecture, and I hope you kind of got the entire context here. We can go through the inference part too. So the English sentence is passed through the encoder as we would during training to generate the context-aware vectors. To the decoder, we pass the start token followed by the padding tokens, and we ensure the padding tokens are all masked in the multi-head self-attention and the multi-head cross-attention. We'll get a probability distribution for the next words, but we just need the first row's probability distribution in order to just get the next word. From this probability list, we can take the first word corresponding to the largest probability, or even perform some form of sampling to generate the next word. And fun fact, the ChatGPT model makes use of this sampling technique, so the same words aren't always generated in verbatim. It adds a more human element or aspect to it. Once the first word of the Kannada translation is generated, we pass this word along with the previous start token as input. We update the paddings and mask for the self-attention and cross-attention components, and generate the second word. And we repeat this process until the end token is generated to get the complete Kannada translation. Now that we've taken a look at this complete architecture in all of its glory, we're actually going to code out each and every single one of these components in Python. And to do so, let's start with the transformer encoder. To help me kind of explain all of this, alongside the code, I also have a runnable Google Colab notebook, which I've executed and have run on just some sample input just to get an idea of which layers are run and how large the shapes are for every tensor as they pass through them. But don't worry, I'll probably be explaining these bit by bit. So in order to get started, let's just start with some basic parameters that we're seeing here. dmodel is going to be the size of every single vector throughout the encoder architecture. And what I mean by that is we have, for example, in this transform architecture, we have my name is Ajay. Let's say that we want to translate from English to some language, French. We'll be passing all of these simultaneously through the transformer encoder, and eventually we're going to get different vectors here for every single word. More technically, this would be a word piece, or it could be characters, but I'm just saying words as just an example here. Now, the size or the number of numbers for every single one of these vectors is going to be 512. And not only that, but if we kind of blow up this architecture, we're going to see that, let's say we have my name is Ajay. Each of these is represented by vectors, which will inevitably become 512 dimensions. And we also kind of see this throughout, that all of these vectors, you'll see, whatever we do, we'll add eventually something called positional encodings. It'll also be 512 dimensions. And this is going to be like 3 times 512. So every vector that you'll see kind of throughout the encoder architecture will be somewhat related to 512 dimensions. And this is the reason why I've just defined it as a parameter here. The next is the number of heads. So the number of headed attention. Now, in the transformer neural network architecture, we see these multi-headed attention units. Well, essentially, when we're performing the concept of attention, we are actually going to perform it 8 times in parallel. And this can be represented in this figure over here, where you'll see that we'll construct, like, let's say, query vectors, key vectors, and value vectors over here. And we'll get all of these vectors. And then eventually we will there's going to be 8 operations that we perform simultaneously, where we take the softmax and perform all of that good stuff with respect to attention. So essentially you can consider this as the number of parallelized operations that we perform within the encoder. Next is drop prob. Now, throughout this encoder, we're going to be performing something called a dropout, where we're going to randomly turn off certain neurons. And what this allows the neural network to do is it forces it to learn along different paths over here, and thus make weight updates accordingly. This will help the neural network be better able to generalize data instead of accidentally memorizing specific data. And effectively, this acts as a regularizer, if you've heard the concept of regularization, for neural networks. And it's pretty useful when it comes to very deep networks with a lot of connections and parameters. Now, I've set this probability to 0.1, which basically means that there is a 10% chance that a given neuron will be turned off on a given stage. We can adjust this value to be anywhere between 0 and 1. Now we have batch size, which I've just set to as 30. So when we're dealing with neural networks and we want to perform some training, typically we would pass in multiple examples at the same time. Those multiple examples constitute a batch. And there's actually a couple of reasons why I would do this. So first of all, it's faster training. And second, it's also more stable training. Now let's take a look at this diagram over here, where this is the contours of a loss function that we see as the concentric circles, and we want to get down to the red point. So you can imagine these outer contours are higher, and we want to kind of get to the lower point. Now, if we had performed, looked at one example at a time, pass it through the network, perform backpropagation, let the weights update, then that would just be one update. And we would need to do this for every single example. And that's where you get this purple curve, which is stochastic gradient descent, where some examples may be good, and so they'll lead you to the loss, but then the next example may be bad and lead you away from the loss, and it becomes this very noisy gradient update. And we need a lot of them in order to converge to the eventual red point. Now, on the other hand, if we had taken batches of data, like if we had basically batched all of our data together, put it through the network and be like, first look at all of these examples and then you perform your backpropagation, then we would have led to this blue curve. right here. Now, that could be a lot of data to process at once, so typically a good middle ground for many of these machine learning and deep learning problems is to use mini batches. So do somewhere along the middle, where we will batch some arbitrary number of examples together in order to just learn effectively, quickly, and also in a way that's more stable. So that every time that you'll see examples, you will see that the loss on average will always decrease. And so in this case, for now, going back to our screen, it's saying that we are going to look at 30 examples of, let's say, 30 sentences in some English language. And it's only then that it's going to propagate through the entire network, that is, go through the encoder and the decoder. Then we have a loss function, which is going to be computed. And then the gradients are going to be calculated in the reverse direction, and we'll have gradient updates. All the parameters will be updated only after seeing 30 examples. And so we have like a mini batch gradient descent that we're going to be performing. Next is max sequence length, this is the largest number of words. In our case, words. Let's just say that we're translating from English to French. So it's the largest number of words that we can be passing in at a time through the encoder. Now, in reality, this is always going to be the number of words that we pass in through the encoder. Because if we actually look at the blown up architecture, if I just go all the way to the beginning over here, you'll notice that if we pass in my name is Ajay as the input English sentence, of padding tokens here. And this padding token will be, let's say, if there's the maximum sequence length is like 200 words and the sentence is only 4 words, and there'll be 196 padding tokens here that are just going to be passed in. And this is always going to be the case where we'll have a sentence and then we will add some padding tokens such that the maximum sequence length is achieved. So there's always a fixed length input for any kind of sentence that we decide to input to our transformer encoder. The next is FFN hidden. Now, when we actually look at the architecture here, we have like a feed forward network. While most of the cases, like throughout the entire encoder, and even like through almost all the entire decoder, we will have 512 dimensional vectors, like I mentioned before. It's only at this step over here that I'm going to be expanding the number of neurons at some point to be 2048 before making it eventually back down to 512. And this is simply to just learn additional information if and while we can, like any other feed-forward layer is designed to do. Now, num layers over here is the number of transformer encoder units that we want to include in our architecture. And if you look here at our diagram, you'll see that there's this n times whatever this is. So this is n is the number of transformer layers because these are typically repeated. So we have inputs going in, we'll have it pass through the encoder layer, and then we'll have it pass through another encoder layer, and then another encoder layer, and then another, maybe as many times as you want to, and then it's passed into the decoder, which is also repeated in this case n times. So we will repeat it again, like if in this case it's 5 times, we'll repeat the decoder 5 times before eventually coming out with an output. And so in our case, I've defined n, the number of layers, as 5. And this can vary depending on complexity. So you can change this to a higher number if you have a lot more data, and also it can pick up more complex patterns. Otherwise, you can also keep it pretty low. Now we'll take all of these values and we're going to create an encoder object by passing it into the class defined as encoder, which I'll scroll up to, and passing all of these values. So let me just take a look now at that same code over here, because I think it's just easier and cleaner. So we have this class called encoder, and in this case, we have this is the constructor, and this is a forward method. Now, every class that we consider here as a part of a network typically will derive its subclass from module. So module is like the superclass, the class in which it inherits from. Now, the reason why we will inherit from this module class is that it allows us to perform many operations behind the scene that are required for learning. So for example, for one, it actually provides its own forward method, and it also helps us, take our tensors, for example, and we can add it to, for example, CPU and CUDA, where we can do like CPU, where we might need to take our tensors, put it on CPU if we're doing inference, or we need to put it on CUDA for if we wanted to do some model training. And it also helps us access like parameters a lot better, where we can take, for example, let's say, let me go here and see, we can get our parameters and also even modify them for initialization purposes. So Module basically provides a lot of that bootstrap code for us that we don't really need to worry about. It also helps us, if we want to save checkpoints, it's easy to do so using these modules where we've trained, let's say, for like 100 iterations, we want to save the model. Defining modules or extending classes from modules makes it very easy to save the state. And for those reasons, we would want to use modules. And so we extend modules here. And because we extend modules, we want to override the forward method. Now, in our constructor though, right here, I've defined this sequential here. So this sequential unit is essentially going to take all the comma separated values here, and it's going to execute them in the forward pass one at a time, one after the other. Now, the way I've defined this is, well, for the encoder contains multiple encoder layers. In this case, it contains like 5 encoder layers because here num layers is going to be 5. And so I will call encoder layers, which I will explain very soon. And I'm going to execute this 5 times. And here you'll see I'll have a star in front of a Python list, which will basically take the list and it will deconstruct it into its component 5 elements. And then we're passing it into sequential. So now we have a sequence of 5 encoder layer objects. Now we are overriding the forward method. And when we override a module's forward method, what happens is that it'll take an input and it will propagate that input for the forward propagation step, where we will pass it into our layers, which we've defined here. So essentially it's passing it through all of the 5 encoder layers. And then we'll have an output over here, which I've just overridden as X, and we're returning that value. And so that will be the overall output of the entire transformer encoder. And so I hope now you understand like what's going on now at a high level. We can now dig deeper and deeper and go at the lower level layers. So for example, what is this transformer encoder layer that we see here? So to see that, we'll scroll up. Now in our encoder layer, we have a constructor again and a forward method, which we use for the forward pass. Now in the constructor, we'll first start every constructor out by calling the superclasses constructor so that it defines everything in the module. So all the module components are now set up. Now multi-head attention is going to be performing the multi-head self-attention of the encoder. We then have layer normalization, which I will explain shortly. We have dropout, and then we'll have the feed forward layer, and then one more layer normalization, which I am which I have defined individually, and then another dropout. I've arranged this forward pass, and I've arranged all of them in a way that it's kind of very similar to looking at this diagram. So you can just see this rectangle is the encoder layer, where if this is X, this input is X, you see that first we will take a residual value. We'll just save it because we need it later. We'll then pass it into the multi-head attention, followed by add and normalization. So we'll take the residual X, then we will then pass it into the multi-head attention. In this case, I'm passing a value called mask to the attention layer and set it as none. This is because the process of attention requires paying in self-attention specifically, let's say that you have all the words in the English sentence, it's going to pay attention to all of the other words. Since all of these words in the encoder are passed in simultaneously, we don't need to pass in any masking. There's no need to say, oh, we can't look at some words in the future, because we kind of already have all the words of our English sentence if we wanted to translate it to some other language. And so I'll explain this in a bit, but for now, the mask actually is just set to none because we don't really need a mask here. It's optional. And then we'll perform dropout, which is randomly turning off the neurons. We will then add the residual connection to this current value, and then we'll perform layer normalization. So this is the equivalent of add and norm that we see over here. We'll then take this output, whatever this is, x again, we'll pass it through a feed forward and do some add and normalization. So let's take the residual, pass it through a feed forward, do some dropout, just to randomly turn off the neurons, and then we perform add and norm. And eventually, we'll now get the output of our encoder layer. And so I hope that looking at just this is a good representation of what this image here looks like. Now that we have a little bit of a higher intuition of like the encoder layer, let's actually pick these individual units apart and see what they're really doing. And let's start with the biggest multi-head attention class over here. Now, in order to understand multi-head attention, I think it's actually best to start with the scale dot product operation, which is like the single head attention, or the core or crux of the attention mechanism. So let's get started with this. Now, if you look at the original paper here, and I'm going to scroll down to this section, you can see that the core attention matrix can be represented mathematically as a softmax of, let's say, this Q vector, which is a query vector, times the key vector. We'll scale it, and then we'll perform a softmax and multiply it by a value vector. So this attention matrix, essentially, when we're talking about query, key, and value, essentially every single word is going to be broken down into three vectors. That is a query vector, a key vector, and a value vector. Now, the query vector is what am I looking for? The key vector is what do I have to offer? And then the value vector can be considered as what I actually offer on attention. So I think the distinction between the key and the value, it seems a little fuzzy, but I think if we look at the code, it's going to be a lot more clear. Now, this here is the attention function where it takes in a query key 4. Now, in this case, our query vector for one attention head is going to be 64 dimensions. And so this will be like 64. I'm going to write this out entirely when we're just doing a pass for just looking at the layer sizes themselves. But for now, just say that this is just a constant and this dk is like some value called 64. We then now perform the matrix multiplication of the query and the key. Now, this key vector is actually not just for one word, but it's for all words for this one head. So this might be a tensor instead. So this is going to be like, it's going to have like a batch followed by sequence length and then some encoding value. And we need to here only perform the transpose by only flipping the last two dimensions. To understand this operation, let's say that we have like some tensor that's 30 cross 200 cross 512. Now, in our case, this is the batch dimension, cross the maximum sequence length, cross for every single word, what is the embedding dimension length. Now, if we just do a transpose of this, we'll notice that all of these values are just inverted. All of these shapes are completely inverted. But if we use a transpose -1, -2, it's only going to take the last two dimensions over here and flip them. And that's why we have a 30 cross 512 cross 200 instead of a 30 cross 200 cross 512. And so that is exactly what's happening to the key vector over here. And now we multiply both of these in order to get the attention matrix. So essentially, for your reference right now, this is going to be a max sequence length cross max sequence length tensor, along with an additional batch dimension. And we are scaling this value with respect to a constant, which is the square root of dk. Now, the reason why we're doing this, we can kind of see in this Colab notebook. So let's just say we have a query, a key vector, and then the query times the key vector. And for each, we're going to determine the variance of the examples that are within them. So in the query vector, it's like 0.68. It's kind of close to 1, kind of close to 1. This one's well above 1, though. The query times key. That variance is pretty large. And also the mean is closer to 0 for all of them. Well, just keep in mind this is negative 0.04. Now, if you scale these values, though, you'll notice that, well, the query and key, nothing changes, but this query times key now also has a variance of the order of 1. And its mean also actually has a variance that's it's 4 times smaller than this. It's closer to 0. And so what scaling allows us to do over here is to ensure that the variance of values within these matrices have kind of like a mean 0 standard deviation of 1. And this allows us for easier and stable training. Now, what I mean by this is, let's say that we perform back propagation, right? So we did a forward propagation, we have some values, we now do some back propagation. And there are going to be, if there are extremely large values here, that can affect the size of our gradient step. And so what we want to do is make sure that these values are as nominal and normalized as possible so that we have stable steps that we take during training. And we won't have like obscenely large or obscenely small values that are propagated throughout the network that affect these gradients negatively. And so it's just stable learning. Next, we have an optional mask, which we pass through a scaled tensor. Note that when we're passing a mask, we don't need it for the encoder. But in the case of a decoder, there are situations where, we have an input where we pass in simultaneously, but technically we don't know what's going to be the output for the next word because we're generating them one at a time. And in order to deal with this, what we'll do is we'll create a mask that kind of looks like this, where we'll have a mask that has let's say this is for the output of a French sentence, where let's say that it only has 4 words. So this would be, some output French sentence here, and this would be 4 words of the output French sentence of self-attention. Now, in this case, though, in training, we have access to all of the data. So we can see everything, but we shouldn't be using all of that data during training because that's considered cheating, because during inference time, we don't know what the next word is going to be generated. When I'm generating the first word, I only know about it. When I'm generating the second word, I only know about them. And that's why you can see that when I know the first word, I can only perform this attention for that first word. For the second word, I can pay attention to the first 2 words. And then I can pay attention to the first 3 words for the third word, and pay attention to the first 4 words for the fourth word. And so this is going to be more relevant when I talk about the decoder in a separate video. But for this video, you don't need to worry about this mask at all. It's also considered an optional mask if we wanted to pass it through the encoder. Next is that we are going to then perform attention. So when I say attention here is that we'll take all of the values of this scaled, and then we are going to perform a softmax so that we get probability values of how much should we focus. And the way that looks here is that we'll have initially this, let's say this matrix right here. This is the scaled matrix with applied mask in this case. But if we apply the softmax operation, you'll see that all of the rows will add up to 1. And so this is basically saying the first word should focus 100% on this word. The second word should focus 51% on the first and 48% on the second. And so on for the third word and the fourth word. So now these are interpretable probabilities of how much we should be focusing on. And then we're going to multiply all of these attention values, which are now probabilities, with the value matrices. So this is now going to give you a new set of tensors for every single word. Now what these new values do is for every input word, we'll now have a new value vector, and that value vector will actually have all the information associated with context. It will know how much attention it needs to pay to all of the other words in that sentence. And so you can consider this value vector for the words to just have more context awareness and hence be of higher quality than just the inputs. Now, this here is the code for one attention head, but when we're actually executing the forward pass for multi-head attention, you can see that only happens at like one stage here, and we kind of have to prepare the entire input in order to split it up into these multi-heads. So what are we doing and how are we doing that? So I'm just going to put some numbers here because I think it's going to be useful, where we have this D model is going to be 512 dimensions. The number of heads, this is going to be 8. Now, the heading dimension here is going to be 512 divided by 8, which is 64. Then we'll have the KQV layer, which is going to be a linear layer of D model cross 3 times D model. The linear layer is basically like a feed forward layer that is used for forward propagation. And in this case, typically in theory, let's go back to our encoder architecture over here. In theory, we would have like all of the input vector, dimension vector, we would split it up into query, key, and value vectors, and then perform their operations like so. However, in code, what we would do is we would kind of like perform all of these operations in parallel, but within the same tensor itself. So they're not like 3 individual vectors, but they're all just 3 like stacked tensors. And so what's going to happen is that this is going to be like 512 cross whatever 3 times 512, which is 1,536, right? And then this is also going to be x512. And so when we pass where we're going to have batch size, cross sequence length, cross D model, this is the input. So in our case, it'll be, what is the batch size? This is going to be like 30 cross 200 cross 512. We then pass it through the query key and value layer, which is up here. And so we're going to get, for every single one of these, we are going to get, for every single word that we have, we're going to have 3 vectors of 512 dimensions each. And so that'll be 30 cross 200 cross, well, instead of 3 times 512, it'll be 1,536. Then we're going to reshape it, though, to be batch size, which is 30, sequence length. Now, we want to break out this last dimension into these parts, because right now we have the query key and value vector, but we want to break it up into 8 heads. The number of heads is 8 times the heading dimension over here is 3. It's going to be 64. So it's 3 times 64 for every query key and value vector, which is 192. So we've now broken up the query key and value into 8 heads. And now I'm just going to switch up basically the dimensions over here. So it's 30 cross 8 cross 200 cross 192. And that's how it's going to look because we're switching these 2 dimensions here. Now, what this chunk will do here is it's going to basically break this entire tensor of this shape into 3 parts. And the way that it's going to break it up is in accordance to the last dimension. So we'll have now QKV vectors where, let's just say each are 30 cross 8 cross 200. Let's just put a cross over here. Cross, instead of 192, it'll be 192 divided by 3, which is 64. That's QKV. Each of them are this. Now, let's actually take these values over here, and if we pass it now into our scale dot product attention, let's revisit this just to see how what we're actually looking at. So just to see this, let's say QKV, and they are going to be 30 cross 200 cross, what did I say here? That would be, it would be 30 cross 8 cross 200 cross 64. So let's just copy and paste that right over here. Now what we're doing here is this last size, we're going to say, we're going to get the shape of Q, which will be returning this value, and it will return the last part of that shape, which is 64. So dk is 64. Now, when we scale this is going to basically take the square root of 64, which is 8, and we're going to perform a matrix multiplication of these two operations here. Now, when we perform a matrix multiplication, it's going to be of 30 cross 8 cross 200 cross 64. And then we're transposing just these two layers over here. So it'll be 64 cross 200. And so we are going to end up with a 30 cross 8 cross 200 cross 200 dimensional tensor. Now, this is the batch size, the number of heads, and now this is going to be our little precursor to our self-attention matrix, because it's number of sequence, that's the max sequence length, cross the max sequence length. So this is the precursor to our self-attention matrix. Now, this mask here, I've said broadcasting to add because in PyTorch, you actually don't need the exact same dimensions that you're adding when you're adding tensors. So for example, this mask is actually going to just be probably a 200 cross 200. But because we're adding in this way, we are actually going to be, PyTorch is pretty smart in that it's going to just add this 200 cross 200 matrix to every batch and every head. And so it'll apply it everywhere in parallel that we need to. So essentially, we're going to end up eventually after this with the same matrix. Even if we were to do, some masking, we'll still end up with the same shape. Now, attention here, it's just applying a softmax operation. And like we saw before, if we kind of scroll to the self-attention here, you see that this was the before shape. And then after you apply attention, you'll see that this is the after shape, and nothing has changed. No shape has changed at least, except the values themselves have changed. We'll come back here, and it's essentially going to be just the same shape. Now, the value is going to be a matrix multiplication of the attention matrix cross this value tensor. Now, we know that this attention matrix is this shape, and the value tensor is of this shape. So what we're going to do is we have it for every single batch, for every single head. We are now also going to have, it's going to be attention that's 200 cross 200. And then if we multiply that with 200 cross 64, we're going to get a 200 cross 64. So what this is for every batch, for every head, for additional embedding. That is the value tensor. And we're going to return both of these two back. So let's now go back to the logic where, let me copy this over. So now we have an attention and value matrices. So we'll have attention is going to be this, and then the value is going to be, let's just copy this, which is essentially the same thing but 64, just for our reference. Now we're going to reshape the value tensor to just be this dimension. So let's see if the math works out here. So that's batch size is 30. The sequence length, this should actually be the max sequence length over here, which is, this is going to be 200. And then the number of heads is going to be 8 times the heading dimension, which is going to be 64. So 8 times 64, that's 512. And if we compare it to our old value tensor over here, that's 30 cross, well, what we're doing is we are essentially taking this 30, we're taking this 200, but we're multiplying 8 times 64 to be 512. So a little bit of a rearrangement is going on. But essentially, we now essentially have what we actually input to our function for multi-head attention. So whatever goes in, the shape also comes out. And so this entire out vector over here is just going to be kind of like this X, but just way better in terms of contextual awareness. And it's because that they have like the same kind of inputs and output shapes that we can cascade them one after the other as many times without worrying about like disrupting some code logic here. Now, multi-head attention is now going to return all the way to the encoder layer right here. So we input, I should have said this too over here, where it's going to be 30 cross 200 cross 512, but essentially even after self-attention, we're going to have the same 30 cross 200 cross 512. Now, dropout, nothing changes. It's just going to randomly turn off neurons, and when you randomly turn off neurons, it doesn't really affect the output. And then we're going to perform layer normalization. So let's actually get into layer normalization. As any kind of module, layer normalization has a constructor as well as a forward pass for forward propagation. Now, parameter shape will actually tell us along which dimensions typically, this is going to be your embedding dimension. So in this case, it's going to be like 512. And that will be like the dimension itself. Now, EP some division over here. Like we have a standard deviation where we have this epsilon, and this is going to be a denominator. So in case that the standard deviation becomes 0 at some point, it's to prevent these infinite values that might occur because of division by 0. Gamma and beta. Now, these are two learnable parameters that we are going to, as the network learns, it's going to be updated continuously. In this case, they're going to be 512 dimensional tensors. Both of them are 512 dimensions that we'll just define over here. Now, this gamma is effectively going to represent like a standard deviation of values, whereas beta is going to represent the mean of values that we'll be applying, that will be, learned continuously during, as we get more and more examples into the network. So now when we take our forward pass, we'll provide some int size cross max sequence length cross 512, which is D model. Now this dims over here is going to be just the length of parameter shape. In this case, it's going to be just like -1, I believe. That we're just basically saying this is the last dimension along which we want to perform layer normalization. And that is true. We want to perform layer normalization on the layer dimension. So what we're going to do is we're essentially just going to take the mean of all of the values. Let's say we have a word vector, right, of 512 dimensions. We'll take the mean of all of those values, and we'll get only one value, right? So that's exactly what we're doing in this step. And keep dimensions true would be that, well, instead of getting a 30 cross 200, we will get 30 cross 200 cross 1, because we want to keep all three dimensions here. And that's why we set it to true. And now we compute the variance, which is basically taking every input value, subtracting the mean for that layer, and then we're going to take the overall mean, and that will be our variance here. And this here is also going to be another 300. It's going to be 30 cross 200 cross 1. And so our standard deviation is just going to be the square root of the variance, and which is also hence going to be just the same shape because we're just scaling it. Now what we're going to do is take every single input in that dimension, like 512 dimension. We'll subtract the mean of that 512 dimension and divide it by the standard deviation of that same dimension. And what this allows us to do is now come up with an output that is, again, 30 cross 200 cross 512. But every single one of these, word vectors is now going to be layer normalized. So it'll have values such that, the mean is 0 and variance is going to be 1. And this is the same concept as like normalizing your data, and hence the name layer normalization, because we're normalizing data by the layer. Now, when we're applying layer normalization, though, this is only applied to like a single sample or at most a batch of samples. But we want to make sure that these numbers are applicable for across the training set. And so that's kind of why we have learnable parameters, gamma and beta, that will kind of help us in making sure that we are scaling these values y appropriately so that the eventual output tensor that we get is going to be comparable throughout every single example. And so when we apply, like, let's say self.gamma, we basically multiplied with every single value of y, we are going to get the same 512 dimensional output. And I can put a multiplication with, like, even though gamma is not the same shape, it's like 512, it's effectively going to say we have one value of gamma that is one learnable parameter for an entire batch and for like an entire sequence of values. And so for this entire thing, because we have 512 dimensions, we are going to have 512 learnable parameters in gamma and another 512 learnable parameters in beta. So this concept here, because, there are different shapes, it's the same as broadcasting that I mentioned way up here when discussing like how we're able to add two different vectors of different dimensions. So I hope this makes sense. And now whatever was input, the same shape is output. So let's take this. And now what we're doing here is we would have added the residuals, which wouldn't have changed the shape. And we now perform layer normalization, which we know also just doesn't change the shape. And again, now we're taking a residual connection. Just to repeat, if we go to our case over here, you'll see that, go over to the figure. We're now at this stage over here where we're taking a residual connection. We'll pass it through a feed forward layer and then add and normalize. And that's kind of exactly what we're doing in this step over here. So we now pass it through a feed forward layer, which is essentially going to be TixND model and also that hidden dimension of 2048. So let's actually go to this really quick over here. So we have a constructor, we have a forward method. Now, this is going to be a linear layer, which is 512. 512 x 512, that's how it's going to transform it. And this is another linear layer, which is going to be, or rather 512 cross 2048. And this is another layer, which is going to be 2048 cross 512. We're going to apply ReLU here. No, ReLU here is an activation function. And there are different kinds of activation functions. So activation functions in general, they help neural networks learn more complex patterns. So typically when we say that there is no activation function, that is, without ReLU, a function might have looked like a straight line that just basically passes through. And with straight lines, you're not able to capture as much information. However, if you're able to do, ReLU is an example of a piecewise linear function. So that means it's made up of multiple straight lines. And so it's better able to kind of capture information. And also, it kind of in its own way also acts as a regularizer where it will turn off certain neurons' activation. Now, because this tends to lead to a problem, in some implementations you might see something called leaky ReLU that is adopted that allows some information to be passed through here. And we can also have used like the tanh operation, which would have, constrained the values between -1 and +1. And then we have like the sigmoid activation, which we typically use when we're interpreting probability values on the the last layer of your neural network. So depending on where your use case is, we would typically use these activation functions, and a commonly used one is ReLU, and so I'm using it here. So we have ReLU and then dropout, which don't really change dimensions. And so we have our input, which is again 30 cross 200 cross 512, we then now take it, pass it through the linear layer. This linear 1 is 2048, so it's going to now be expanded to 2048. Pass through ReLU, which means that it doesn't change its shape, but the values will change because it's activated. And then we perform dropout, nothing changes, and then linear 2, which means it comes back to its original 512 dimensions. And so the input shape is the same as the output shape, and that is what we are returning back. And so that's our pointwise feed forward layer. And if we go back here, you'll see what comes in also comes out. So essentially this FFN, or feed forward network, is just going to return the same dimensions. Dropout, like I mentioned, will not change anything. And also layer normalization, which we did previously, will not change anything. And so even here for this entire encoder layer, whatever is we input here is what we are outputting as well, at least in terms of shape. Now, because of all these operations though, like I mentioned before, this new output X is just going to be much more context aware than what was the input over here. And so the control will now return back to, well, self layers, where we're going to execute this same exact process, the same forward pass, like 5 times, because we have 5 layers. And in each case, we're just going to not change the shape. The input shape is the output shape, so we can just keep recurring through them. And then once we finish the sequence, we will end up with the final vectors X that happen to be just really good at just encapsulating context. And when I say really good at encapsulating context, this is only after some training has commenced, as it just gets better and better as we look at examples. Now, all of the shapes that you see that I've mentioned here, I think I've covered all the shapes that can possibly happen here. All of them are actually written out in a flow right here when I execute it on dummy data here. So you can kind of see the flow controlling going from attention to dropout, layer normalization, where we start out with the same tensor, 30 cross 200 cross 512. And even after like the sea of operations, you can see that we'll end up with an output of still 30 cross 200 cross 512. All right, so I hope we got now a good idea of how to code out the transformer encoder. So just as a quick refresher, let's say that we're trying to build a translator from a language English to another language, which is in the Indian subcontinent, called Kannada. Now, in order to do this, this is an encoder, this is the decoder. We pass in the English words of the sentence simultaneously. We'll get word vectors simultaneously over here. Then the encoder phase is done. Now we take all of these vectors, pass it into the decoder in this multi-head attention, and we have like a start token that we want to pass into the decoder, and we'll generate the next word. This word is then passed in right here to the beginning, and we generate one word of the decoder at a time. So how does the decoder actually do this? Well, we're going to talk about that exactly by blowing up this entire decoder architecture in terms of code. So first we're defining this D model, which is essentially the size of all the vectors internally within the entire transformer neural network. And I define it to be 512. So that means that each word is represented by a 512 dimensional vector. The number of heads here is the number of attention heads that we want when we're performing multi-headed self-attention as well as cross-attention. Drop prob is a parameter that we use for a dropout, which is the randomly turning off of neurons. And this random turning off of neurons in a network helps the network learn along different paths and helps it generalize better. Batch size, this allows computers to process multiple, in this case, sentences together all at once. And this enables faster training, as we're not typically just, in the stochastic gradient descent updates, we would pass some input to the network, generate an output, generate a loss, perform backpropagation, update millions of parameters. And this is only after seeing one example, and we have to keep doing this for every single example we see. But with batch gradient descent, we only need to update it, let's say, in this case I set it to 30. That means only when we see 30 sentences, which we pass in all at once, It's only then that we perform a batch update. And so now you'll see that like the batch updates don't happen very jagged. They happen much less frequent, but also more smooth. Next we have is max sequence length, which is the maximum number of tokens. In this case, tokens are words that a sentence can have. And I've set this max token to be 200 to be like, okay, the maximum number of words in the English sentence that we can possibly pass is 200. And the same also goes for the output Kannada sentence. I've just set it to be the same value, but they could be different values. FF hidden, in the entire network, we're gonna have like linear layers that occur. And whenever we do have linear layers, I want the output number of neurons in the hidden layer, and that specific feed forward layer is to be 2048. This is just a hyperparameter that I found in the paper Attention is All You Need, but you can essentially set this to whatever value you want. It's just for the propagation of information. Next is num layers. This is going to be the number of encoder layers and decoder layers that we want on repetition. So if we go to this diagram of here, essentially this n I am setting to 5 because they're both the same. So essentially what's happening is that we pass some inputs to the encoder. It's essentially going to go out here, but we're going to have a cascade of these encoders, one after the other. So you can imagine just like 5 of these encoders stacked on top of each other. So inputs go in, it passes through all 5 encoders, then the output goes to the decoder over here. And then in the meantime, we also have like the Kannada language output, or in this case, it'll be input to the network. It goes through this decoder and it passes in 5 times before it eventually generates some output probability and hence predict the next word. Now, why do we have like a number of cascaded layers here is to deal with the complexity that language has. So the more complex the patterns could be in the language itself, the more intricate you would want your architecture to be so that it can capture those patterns well. And that's kind of why we use like a multi-encoder layer, multi-decoder layer transformer neural network architecture here. Now, X here is the input that we would see to the decoder, but it is the English sentence. So you can imagine X is going to be just, after we pass some inputs, we get some positional embeddings, we pass through the encoder, it will now be context aware. Every single vector is context aware, and those vectors are what X constitutes, and we'll be passing it in here later. Now, I have like almost like some similar thing, which is Y, that I've generated over here. That is batch size cross max sequence length cross D model. So this is essentially also a sense of like every single word has been encoded into a 512 dimensional vector, but this is merely just the input part. So Y is simply like this stage right over here. At this point, I've just generated some random values, but they would actually come from some, data set, and we would have transformed it. For this video, it's a little too much code, but I will show this in subsequent videos for sure. But for now, just to get the use to the entire flow, I've introduced it here. Now, this mask that I'm creating over here is actually going to be a look ahead mask. This is required because during training, we pass all the words of like the target sentence at the same time, but we don't have information about every single word in that sentence at the time. And so we would need to mask some inputs so that we can prevent ourselves from cheating and looking ahead. And so we would create a look ahead mask. If you're curious about how that mask looks, it kind of looks like this, where we have for every single, this would be a 200 cross 200 tensor, where we have, for the first word, it's like saying that we don't need to mask it. Zeros are don't mask, negative infinities are mask. So for the first word, it's allowed to see itself. The second word is allowed to see itself and the word before it. The third word is only allowed to see the stuff that happens before it, and so on until the very end. So this kind of prevents cheating from happening, and hence will prevent a situation where the decoder performs well during the training time, but terrible during the test time because of data leakage. And then we now pass in all of these values, calling the constructor of the decoder class, which we will take a look at. And then we call the model's forward pass. And for the forward pass, I've done a lot of print statements over here. So you can kind of see exactly what was the dimension of every single tensor that occurs. And I will provide this code all in the description down below. But in this video, I'm also going to explain why these dimensions are the way that they are. So I've pasted all of the decoder code actually right here in the Colaboratory notebook. So this code over here and this code are the same. And so I'll just be using whatever's in the decoder Colaboratory notebook. Let's start with the decoder class here. So I've defined a decoder class to have a constructor, which takes in all the parameters that we just mentioned before, as well as a forward pass. Now, I'm overriding this torch modules because module itself is a PyTorch extension that provides a lot of the underlying boilerplate code that's required for creating neural networks. This includes like performing backpropagation, it performs like memory management, and also managing like whether like tensors are supposed to be on GPU during training time versus on a normal CPU machine during testing time. And it also facilitates model forward passes too. And so, because of all of these nice little intricacies that Torch provides, I use Torch modules over here. And because we use Torch modules, we also can now provide a forward pass. And we can do things like call this entire method directly, as if it were just a method. This would instantiate, in fact, the forward call or the forward function. So when we call the forward pass, we have the English sentence, the Kannada sentence, as well as the mask. So let's actually write out all of the shapes of these values so that we can kind of walk through its execution. So X is going to be the English sentence, which is going to be 30 cross max sequence length, which is 200 cross 512. And we can say the same thing is going to be for Y as well. Y is also going to be the batch size, which is 30 sentences, cross 200, which is the max sequence length, cross 512. And then the mask itself, at least for this simplistic case, is going to be 200 cross 200, which is max sequence length cross max sequence length. Now we're going to be passing this into layers. So layers here is a sequence of, decoder layers. So essentially, if you look at this figure over here, this here is one decoder layer, but it's repeated n times. And so if this is under a class called decoder layer, we repeat this n times, that will be what self.layers is, essentially. Now, typically you would use something called torch NN sequential. That looks kind of like this right over here. But here you can see I'm using sequential decoder. And this is mostly because when I want to call the forward pass, if I had used just sequential on its own, you cannot pass in more than one parameter. And because I have more than one parameter to pass, I need to pass in a mask, for example, that's kind of why I've implemented my own sequential decoder, because I just can't use this directly. So it extends sequential. And what it'll do is I'm just going to take this input, but when I'm calling every single decoder layer, I'm going to be passing in all of these parameters, but I get the new value of the Kannada outputs, that is the output sentence, every single time. And I just keep feeding it back into this module. But the same value of X, that is, from our encoder, that is the English sentence, is just passed in regardless of which decoder layer that we are looking at. And thus, sequential decoder thus becomes an array of these decoder layers. Let's just actually take a look at what each decoder layer looks like. So if you scroll up here, you can see also decoder layer. It extends, torch modules, and hence it also has a constructor and a forward method that we can call directly. Now let's again walk through the forward pass, and I'll describe each of these as and when they appear. So first of all, we're assigning this here to this underscore y, and this is going to be used for residual addition. So you can kind of see in the normal paper here, you see that there are these arrows over here. These arrows are essentially skip connections or residual connections, and you would typically see these in very deep neural networks. This is because as the deeper the network is, as you do a back propagation of your gradients, they become smaller and smaller and smaller, and eventually they might vanish towards the beginning of your network. And if gradients vanish, that means that your neural network will no longer learn. And so in order to propagate a signal much stronger, we use skip connections. They propagate the input signal much better in the forward direction, and also any kind of loss, or I should say the the derivative of that loss with respect to the inputs, they will propagate it very well in the backward direction as well. And so there's always going to be like some gradient update that occurs even for like the earlier layers of the network. And that's kind of why like this architecture uses those skip connections. What we're going to do is now perform the mass self-attention, where we take the Kannada sentence, and we're also going to have, the decoder mask, which is the same 200 cross 200 mask that I showed before. So this self-attention, actually you can see over here, is multi-head attention. So let's go over to that module, multi-head attention, which is right over here. In the multi-head attention, you can see that because this is the Kannada sentence, in this case, it's going to be 30 cross 30 cross 200 cross 512. That's the dimensions, right? That's batch size, max sequence length, and demodel. Now we're going to have query, key, and value. So this QKV layer, if you see here, it's a linear layer that will basically map this 512 dimensions to the 3 times 512 dimensions, which is 1,536. I believe that's the multiplication here. So looking at the decoder architecture, it's kind of like this, where we have batch size, max sequence length, cross 512, and we create query, key, and value vectors for each and every single word. And that's why, since one word becomes now 3 vectors, that's why we see 1,536. So the query vector for a word is, what am I looking for? The key vector and the value vectors essentially are like, you can consider them as some form of memory, or you can also consider them as, what do I have to offer? So it's kind of like its own information that it already knows. So coming back to the code, this is now going to be a QKV, which would be 30 cross 200 cross 1,536, as we've created query, key, and value tensors, which are going to be used for attention. But we are also reshaping this because we want to perform a multi-headed self-attention. So we're kind of distributing this across 8 heads. And because of this reshape, I'm quite literally going to write this out as 30 cross 200 cross the number of heads, which is 8. That's how much we've defined over here. It'll be 8 that we pass through. Cross, if you kind of just do the multiplication, I think it's like 192. That's 192 times 8 will be 1,536. And so we've created 8 attention heads. And if we look at our decoder, why we're doing this is that these are essentially going to be 8 parallel processes that are going to go on. That is, each one of these rectangles, there's like 8 rectangles over here, and each one of them is going to perform its own attention. And then in the end, we're going to be concatenating them together. So coming back again to the code, this is going to be 30 cross 200 cross 8 cross 192. We're just going to be reshaping this. So let's just write this out again. So it's 30 cross, we have the second dimension, which is 8 cross, first dimension is 200 cross 192. That's just as an advent of the reshape. Now we'll be chunking this up by the last dimension into 3 parts over here. So that's 30 cross 8 cross 200 cross 64. That's 192 divided by 3. And this is Q, but you can also say that the key and the value vectors will also be the same. So I can kind of say this is going to be the key as well, and this is going to be the value vectors here as well. Now we perform scale dot product attention. So this is like the crux of the attention mechanism over here, and we're passing each of these query, key, and value vectors along with a decoder mask. So let's go to our scaled, let's copy this because we probably want to know what the sizes are for these. In fact, we'll do that for everything over here. We go over to scale.product attention, which is like this right here. And we'll just copy some of these sizes. And I know the mask was like a 200 cross 200, just to keep this in mind. So DK here is actually just a constant that we are going to be using in a division over here. And this is required to scale the multiplication, the matrix multiplication of Q times K. And we require this because we want all of these values to kind of be with like a mean 0 and standard deviation of 1. And this scaling parameter actually just helps us accomplish that. Now, in fact, we can actually see this in action by I'm in my GitHub repository right now where you can kind of check out all of the code for this video and also like the past videos that I've created on transformers over here. And you can see that we want to perform this operation of self-attention where we have like a query vector and a key vector, which we do like a matrix multiply over here. But now the query and key, the variance is like close to 1, but the variance of like the multiplication of these, you could see that it kind of goes off the charts a little bit, like it's 5 to 6 times greater. However, if we were to scale these values, you can see that the variance now becomes much more tractable. When we perform the multiplication here, we transpose the last layer and the penultimate layer. So that means that we actually make, let's say if this is the key vector, we actually transpose just both of these. And we can't just do like a k.t because otherwise that would transpose like the entire thing. It would be a 64 cross 200 cross 8 cross 30 tensor, which is not what we need. We just want to transpose these last two layers. And so if you do a matrix multiplication of query and key, that would be 30 cross 8. Let's do that. 30 cross 8 cross. And this would be a 200 cross 64 times 64 cross 200, which would be a 200 cross 200 scaled tensor. In this case, it's scaled, but this is just a division. It doesn't change any shape. So this is kind of like the initial parts of how the attention matrix is actually going to look. What we do is if mask is not none, in this case, it is not none, we're going to add this mask. And we're adding a mask of 200 cross 200 to this tensor. So even though it is a different shape, PyTorch supports something called broadcasting, where the last dimensions here match the last dimensions over here. It's still a valid addition, and it's just going to add the same exact tensor or apply the same exact tensor to every single one of these elements. So there's like 30 times 8, which is like 240. So it's like for every batch, for every head, we're going to apply the same exact mask. And so this mask is now going to end up with, it's going to be 30 cross 8 cross 200 cross 200 after the operation of this masking is done. Just note that in this case, this is a look ahead mask, but we could have also added some padding to this same mask, and we would have still ended up with the same dimensional tensor once the entire, operation was said and done. Next is that we perform softmax. Now, softmax is just like taking exponentials and dividing it by the sum of exponentials, which essentially does not change the dimension of anything here. The attention matrix is still going to be the same dimensional shape. It's just going to do the softmax on the last layer, this last layer over here, so that every single row is now going to add up to 1. Now, the values here is going to be a matrix multiplication of the attention and the values vector, which is, this is the attention, and the value tensor looks like this. So this is going to end up with the shape of 30 cross 8 cross 200 cross 64. Right? And this is just for one attention head, and we're going to be returning both of these. So in the self-attention case, this attention is going to be how much attention are we paying for every single word on itself, whereas the values is going to be, well, what are the actual context-aware final tensors that we are looking at right now for every single word? So that's for every batch, for every head, for every word. We have a 64-dimensional vector that represents context of that word. And eventually, when this logic returns, we copy this over. We'll come back all the way back to multi-head attention over here. This logic will return, and both the value, this is the values tensor. And now we're going to, well, reshape this such that we flatten the heads dimension as well as, this 64 over here. And so this would be 30 cross 200, that's max sequence length, cross 8 times 64, which is 512. And so effectively, we are concatenating whatever we found from each and every single one of the 8 heads together. And then we have this output that is just going to be passing through a linear layer. And this linear layer actually doesn't even change the dimensions. It's like a feed-forward layer that maps like 512-dimensional vector to another 512-dimensional vector itself. And so we have the same shape over here. So I can just copy and paste that over here. And it's this now that is passed out. So interestingly here, Because this multi-head attention, you can see like it's the same input shape that was input, same that was output, and so it can also be a repeated layer without like disturbing anything like very jarringly, like, oh, the shapes don't match. You won't be getting like such errors here. So now once that multi-head attention is complete, the control is going to now transfer back. So self-attention is now complete, and the output is this shape. Now we perform dropout. Dropout, as I mentioned before, is the random turning off of neurons so that the neural network can learn along a more generalized path, better for generalization, and hence it doesn't memorize. So it's the same shape, it's just an operation though. Next is add and layer normalization. So we can add whatever we saw here, which is the same shape essentially. This was the same shape up here, this underscore y. We add these two together and then we just normalize them with layer normalization. So let's go to norm 1. Norm 1 is layer normalization, and we pass a parameter shape over here called, well, parameter shape, and we pass 512. So let's actually look at layer normalization for a little bit here. Going up to layer normalization, all right. So we have like this DIMS over here, and this DIMS is gonna be along which layers do we actually want to perform layer normalization. The entire goal of layer normalization here is for constraining the values of every single layer to be with like a mean 0, standard deviation 1, and this helps stable training so that we can jump, you know, the jumps that happen during like every single training phase and gradient update phase are pretty stable. They're not too erratic. And so this here is going to be, I believe, DIMS is going to take on the value of just the last layer. So it's just going to be like a list of -1 in this case. That's what DIMS is. Next, we're going to compute the mean along this last layer. Now, the inputs, just for clarity, are going to be of this shape, which is 30 cross 200 cross 512. That's exactly what we're passing in. So we're taking the mean of all of these elements here, that is all of the 512 dimensional vector that represents a single word. We're going to take the mean of that, and we say keep DIMS is true because if you just take the mean of these and you run this operation, it's going to just return a 30 cross 200 dimensional tensor, but we want a 30 cross 200 cross 1 dimensional tensor so that we can perform some other operations down here so that there's like the tensor shape dimensions match. So one step at a time, we take the inputs, which is the shape, we'll subtract it for every single mean. That means that every single word is going to be having there's like a single mean that we have computed, and we're going to subtract basically that same mean value over here. So you're going to end up with the same dimension over here. And so this is going to be the same dimension, that's the variance, and standard deviation is simply the square root of that variance, which also doesn't change the shape over here. And the output, hence, also doesn't really change at all. The only difference is now this y is going to have much more normalized values, where the mean is 0, standard deviation is 1, and hence allows more stable training. But what you see here too is there are some gammas and betas. So gammas and betas are a set of learnable parameters. In this case, there's going to be 512 essentially of these. That's the parameter shape. So all of these gammas are initialized to 1, and all the betas are initialized to 0. So there's essentially 512 gammas and 512 betas that will be learning over time. And the goal of these learnable parameters is kind of if you've seen batch normalization too, where we have essentially gammas and betas, they help learn along dimensions that are not included in this entire operation of computing the mean and standard deviation. And so even though we do some strange normalization along this 512 dimension, we are trying to make sure that all of these parameters become kind of comparable to each other. And that's kind of why we introduce so many gammas and betas. We have one for every single batch and word that we have a specific gamma value. And so what we do is we multiply gamma times y, that is the value of gamma times every single element in y, and just add beta. So gamma is essentially going to be like a standard deviation. It'll learn to be like a standard deviation across multiple examples. And then beta will also learn to be like a mean across multiple examples, so that it can better, so that like this out over here is better comparable across these multiple examples. And after performing this operation, we still end up, it's still the same shape, right? Now we have the same input, same output shape as well. So when we return the control now from layer normalization, we go back to, where do we go? We go back to decoder layer, and the output of layer normalization is the same shape, right? And we just perform the same operation here, but instead of masked attention, we now perform cross attention, which is slightly different. Now, in this cross attention case, I'm not passing in any mask, since like this is going to be the difference between self-attention and cross-attention, which I will mention actually. Let's just go over here so that it just becomes more apparent as to why we're not passing a mask for now. So multi-headed, this is multi-headed cross-attention. You'll kind of see like the code is very similar to what we saw for self-attention. However, the main difference you'll see is that instead of taking a QKV layer, we have a Q layer that's separate from a KV layer. So every single element that is in your encoder, that is like the Kannada words that we pass in the decoder, they are going to form query vectors. But then we are going to convert every English word that we get as the output of the encoder to key vectors and value vectors. So you can see for self-attention, we created, from the same Kannada words, we have query, key, and value vectors. But for cross-attention, if we go all the way here, now we're performing cross-attention. Let's say that this is coming from the English encoder. This is like the set of English words for the sentences in the encoder. Each word is now encoded into a key vector and a value vector from the encoder. But for the Kannada side, we encode everything just into a query vector. And so while self-attention, every word is encoded into a key, query, and value. In cross-attention, we have the query coming from the decoder, but the key and the value coming from the encoder, and then we perform very similar operations along with no mask in this case. So that's why coming back here, we'll see that like the inputs here, like X is going to be, the same dimension, 30 cross 200 cross 512, and so Y will also be that dimension. But now after passing through the key and the value, again, key, I say every word is converted into like key and value, but essentially they're going to be stacked on top of each other as a linear layer. So we just convert 512 to a 1024 dimensions over here. And so because like every word is going to now have like a key and a value from the encoder side, this is going to be 30 cross 200 cross 1024. Now for the query side, it's going to be 30 cross 200 cross 512. And we're going to now reshape this so that we can perform multi-headed cross-attention. And so the key and the value, let's take this, but instead of like 1024, it's going to be 8 times, this heading's dimension is 64, so I believe it's going to be 128. And we're also going to reshape our query vector too, where the query vector is essentially also going to be multi-headed. So we'll take this, we'll paste it here, and this is going to be times 8, but instead of just 2 times the head dimension, it'll be just the head dimension itself, which is 64. Now we're going to permute the key and the value over here. So let's just take this, but we'll switch over the second and the third places. So that's 30 cross 8 cross 200 cross 128. And the same kind of goes for the query itself too, which is 30 cross 8 cross 200 cross 64. And then we will chunk the key and the value vectors here into just 2 parts based on the last dimension. So we'll take this and we're breaking into 2 parts. So this will be 64 for the key. And then we also have the same thing for the value essentially. And so we have query, key, and value tensors of like the same shape. And this is where we pass this in. Now all through the scale dot product attention again. So if we go back up here, we actually end up with the same shapes, right? 30 shapes essentially in the mask. In this case, we don't have a mask, but all of the operation shapes remain exactly the same. And even if we don't execute this code, it's not like this scaled value, it still maintained its original shape anyways, so it wouldn't matter. I hope that what's clear here is that in the decoder case, we actually don't even need, for the cross attention part of the decoder case, we actually don't even need to execute this unless you put in like a padding tensor as well, or like a padding mask, so that you can ignore some of the padding tokens, which is required because, you know, some sentences might not be as long as like the total length, the maximum sequence length of like 200. But if you don't do that, you don't really need this section over here. It's not going to be executed, and hence it's going to skip over. And these shapes are going to be preserved. So it's kind of exactly what we want. And so what you're going to get is this output tensor over here, put in our value tensor. And now we are going to now concatenate all the heads together as we did previously. And so this is going to be 8 times 64, which is 512. So we'll just reshape that. And this is now going to pass through a linear layer, which is not going to resize anything. It's just for additional information. And so we actually now have an out vector that is going to be, 300 cross 200 cross 512, which is exactly what we input in here. So we copy this. This is multi-head cross attention. So let's go back to the decoder layer. And the output here of Y is still going to be the same shape. Next, we perform, kind of the same procedures as before. We perform dropout, which doesn't change the shape. It just randomly turns off neurons. And we'll also do layer addition with layer normalization, which does not change the shape again. And next, we still have this. So we pass it through a feed-forward connection. Now, this feed-forward network, FFN, I've defined it as position feed forward. Let's actually go to that just real quick. It's actually quite a simple function, so it shouldn't take too long. So we pass it through the input that we have, which is X, is going to be like, it's going to be this shape, right? That's X. We pass it through a linear layer, which is going to map it to a hidden dimension, right? So that's 2048. And then we pass it through rel, change the shape. It's an activation function that will allow the network to better understand and model complexity in your data and complexity in patterns. Typically, like ReLU does have like some issues with like the dying ReLU problem because, for any activation value that is lower than 0, it will just completely shut it off. That's just the nature of the function. And so some other functions like ELU, GELU, leaky ReLU are also used, which you can experiment with too. But for now, we have ReLU, and that doesn't change the shape. Dropout doesn't change the shape. And then linear 2, which is just going to be the inverse of the first linear layer, where we still now get this D model. So let's just write this out, and this will be 512 dimensions, and this is returned. And so at the end of the day, when we do our position feed forward network, we are going to end up with a 512 dimension output here, which is the same as everything that we've seen before. Next, we perform dropout. Like we said, that changes no shape. Layer normalization changes no shape. And we return the value that we get as the output of one decoder layer. And this output is exactly the same dimensions that we input to the layer itself. So we take this value, and this is the decoder layer that we will go over here. This decoder layer, let's just put this in a much more readable way. So this is the output of one decoder layer. So this module executes once, and now we have this Y, which would have been this shape over here. And then we just input that same Y. This has to go num layers. We defined it as 5. So this will execute like 5 times. So now this new tensor, which is slightly more context aware of the Kannada output language, is passed back into this module, and we keep updating Y, which is like the Kannada target tensors for the Kannada words. Now, once all of these are complete, the control will pass back over here, which the output is going to be, well, the same shape, right? And this is good. So the input now matches the output. And from this output, I haven't coded it out here, but it's essentially going to be mapped into a softmax, a linear layer softmax, and from that we can actually compute what the next words could be. So everything that I've kind of like discussed over here, I actually like put so many print statements so you can kind of see like I've printed it all out, and in the end you will see that's exactly what the output shape is: 300 cross 230 cross 200 cross 512. And to see exactly like what happens, in the conceptual architecture, we're essentially way at this stage over here. We have the batch size cross max sequence length cross 512. That's exactly what we see: 30 cross 200 cross 512. Where we now can map it to we can map each of these now to a Kannada word that is human interpretable and perform some softmax to determine what is the word that is supposed to come next. All right, so now that we have a good idea of even how to code each of these components of the encoder and the decoder, now I want to kind of focus on the beginning over here. Like, how are we going to take language and encode it into a format that computers can understand? So let's talk about that now. So in this Google Colab notebook, I have a couple of files here that consists of the English sentence, which is the source sentence, as well as the target Kannada sentence, which is the sentence we want to translate to. Now, if you want to know how that information looks, it kind of looks like this, where this is the Kannada file, where there's about I believe 4 million records over here. That's 4 million sentences. And then we have a train file over here, which is the English translation for every single corresponding Kannada translation over here. So this is "he is a scientist." This is the Kannada translation of "he is a scientist." And we need to kind of clean this file, process it, create a data set, and then feed it to our transformer neural network. So the source of this data set is Samanantar. If you want, you can actually kind of read this paper of what it contains, but essentially it has the English translation. So for every English file, there will be 11 files where you have 11 Indian languages, and those languages are over here, which are short forms of some of these Indian languages. I am using the KN file, which is the Kannada file. And you can just see some more details of what are the number of records, the number of tokens, and whatnot. And also all these they also had benchmark analyses. So I would just recommend that you read this paper for more information. But if you actually want to download this data set, you can hop over to this link, which all of these links will be in the description below. And you can just click on the downloads and then download everything. I will say a big warning is that there is no good way to download just a single part of these datasets. Like I mentioned, there's these files are pretty large. They're gigabytes of data. And in fact, I think you need about 20 gigabytes of data to download everything. And unfortunately, you only have an option to download everything at once and not just Kannada English or Kannada Hindi. So I would just recommend that you have some space on your computer before you try to download these. Coming back to our file, we want to define a start token, padding token, and end token. So a start token is going to be to begin a sentence, end token is to end a sentence, and a padding token is typically used because we want to make sure that even though sentences might be of different number of words or characters, we want to ensure that they are converted into numbers, vectors, matrices that are of the same length, and hence we introduce padding tokens. Next, I'm going to introduce a Kannada vocabulary, which is a set of all possible symbols that we can input and output to and from the model. And the same is true for the English case. It's the number of characters that can be input and output to and from the model. Let's talk a little bit about these individual languages so that we kind of get an idea and a better understanding of what we can expect moving forward for translation. Now, these English characters here, we have a character set that consists of consonants and vowels. And we call this entire set an alphabet, as each character can represent an individual sound. S, K, H, I, and so on. Similar way of we have consonants and vowels. So this first row is a set of vowels, and so is this third row. So that would be a, I, u, ru, I, o, a, ha. Of consonants. So it's ka nya cha cha ja ja nya ta ta da da na ta ta da da na pa 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 ma ya ra la va sha sha sa ha laksha ya. So entire thing, wonderful. Even though we call Kannada an alphabet when just speaking normally, it is technically more an alpha syllabary, where each character here clearly just represents a syllable, at least here, but we can also combine them together. We can combine consonants and vowels to actually create a sound, like a unit here. So for example, this is k plus a, and that becomes ka. This is k plus e, and that becomes ki. This is k plus e, that becomes ki. So we're combining a consonant, which is k, and a vowel, which is one of these, in order to create like different units of characters here. And so Kannada is an alpha syllabary. And like we did for ka, we can do that for every single other consonant and vowel pairing to get a set of these units of consonant vowels. And this is what we call in Kannada a ka gonita. And so since English is more of a phonetic alphabet language, whereas Kannada is more of an alpha syllabary, you can kind of see that there would be some form of complications that can occur when you're translating from English to Kannada. They're very different kinds of styles of writing, so it's fun to keep in mind though. Now for every single one of these lists of Kannada and English vocabulary, we want to create an index. So that's a dictionary that maps some integer to a character that you see up here, or a character that maps also to an integer. And I'm just creating that index over here. Now we're gonna read these files that we mentioned over here entirely from our Google Drive. And we're only going to pick out the top 100,000 sentences for now, so that's faster and easier to train. We probably don't need 4 million, but if we do need more, we can always pull more by just increasing this total sentences value. And I'm just going to get rid of these new line characters that are appended at the end of each sentence, and then just print it out for you. And so you'll see like the English sentences look like this, and their Kannada translations correspondingly kind of look like this. Now, as an input to this transformer neural network, entirely either the inputs or the outputs, we're actually going to convert every single character into some embedding instead of every single word, as we have probably discussed in many videos before. When we encode every single character into an embedding, we want to, ideally it should be a little bit smaller so that there's not too many parameters to learn, inference becomes faster. But over here, you can see that the maximum Kannada sentence, it has 639 characters, while the maximum English sentence has 722 characters. Now, you can go and plot a distribution, but I'm typically sure that you'll see a very long-tailed curve where there might be only a couple of sentences that are very long, and I don't really want to just accommodate all of those sentences that are just super long. Even there's only like a few of them anyways. I would rather just accommodate the majority and try to decrease my dimensions so that it just becomes easier to learn, less parameters throughout the network. And so what I'm doing is I'm just trying to see the 97th percentile of like the longest words. So this is basically saying that there's 172 Kannada sentences in my data set that are less than 172 characters. And there's only like 3% that are more. And with English, we have a very similar size. So what I'm going to be doing now is defining a maximum sequence length. That is the maximum number of characters in a sentence should be only 200. Anything more than that, we'll just get rid of from the data set. And so I've just written little helper functions that kind of just check these conditions, right? Whether they're actually, first of all, whether they have valid tokens. That is, all of the tokens that are present in each of these lines is actually a token of the vocabulary that we've described up here. So only if this is true, and also it has like a valid sentence length that is less than 200 characters, and then those are the ones that we actually use in training the transformer. And so we reduce from 100,000 to just 81,900, which is completely fine. And why it's like such a huge reduction is mostly because both the English and the Kannada sentence translation have to have these two parts satisfied. Next, we are going to create a data set. So PyTorch has a predefined class called a data set, which is required in order to feed data and train a PyTorch model. This kind of takes care of a lot of the boilerplate code under the hood so that there's consistency in how we fetch, batch, and everything else with data. And in this case, since we're working with text, we create a text dataset class, and I want to override, we have to actually override when you're creating a custom dataset, a get item, the length, and also a constructor if you require it. So in my case, this length is going to be used internally by dataset to get whatever the length of the current sentence is. But whereas get item here is going to take in an index and get the corresponding English and Kannada sentence, which we retrieve when we're going to be training. So we're iterating over a batch. We'll be getting an English sentence and a Kannada sentence, and this function is going to be called to fetch that data. I'm creating a custom dataset because this dataset class doesn't really satisfy my own needs. But you can check PyTorch's repository for dataset just to see if what you have is already built in. Otherwise, you can build a custom dataset like we are doing here. And so when you execute dataset and you'll just get, let's say the second element in that dataset, you'll see that you'll return a tuple of the English sentence as well as the corresponding Kannada translation. Now, for the sake of this entire setup, let's just say that the batch size is 3. Now, to explain why we're batching in the first place is that let's say that we just take one input sentence and one Kannada translation as just the batch size. So batch size 1, which is essentially no batching whatsoever. So if we pass in one Kannada sentence and English sentence during training, we'll get some output loss function. And then we're going to be performing backpropagation, update all of these millions of parameters over here in order to now get a new state. And then we will repeat this again with passing another English and Kannada sentence. And again, all of these parameters have to be updated. Updating each and every single parameter for just every single example can take a very long time. And also your loss steps will also be very jaggedy. So in order to speed up this training, we kind of parallelize passing in information to this network. So in this case, I said 3. So we can put 3 input sentences in Kannada and English, pass it through the network, and only after all of these have been read, we only generate a single loss, and then we just backpropagate that loss. So it's only the parameters are updated once for every 3 that are input. So we can increase the batch size to decrease the number of times the entire network is going to be updated, and this will speed up training. And hence, we use typically, for many machine learning cases, we use mini batch gradient descent. Let's just say that we set the batch num to 3. So what you'll see is actually 2 tuples of data. So for the first one, you're going to see 3 over here. There's 3 English sentences, 1 that are comma separated, 2 and 3, and then that's going to be up till here. And then you'll see the corresponding Kannada translations in another tuple over here. And that's kind of how the data is going to be given and processed during training. Next is tokenization. So we have these sentences, but we need to convert these into numbers because computers don't understand text, they understand numbers. And so I've created this tokenized function over here that'll take a sentence, and it'll take also whichever language, depending on what you want, either English or Kannada, it'll take that character to number embedding. And it'll take an optional start token and end token, depending on whether we want to pass in a start token or end token. And so if we have a start token, we'll prepend it to the beginning of the sentence. If we have an end token, we will append it to the end of the sentence. And in other cases, we need to have padding tokens. So for the remainder of all of the characters, we are going to just introduce a padding token that we discussed previously. And then just create a torch tensor so that everything, instead of a Python list, it passes a tensor, as everything in PyTorch is processed typically with tensors. So to look at an example, let's just say that we have a batch. Since the batch size is 3, it has 3 English and Kannada sentences over here. Now I'm going to describe some empty lists. This is going to be the list of all English tokens in these sentences and Kannada tokens in the corresponding sentences. Now, for every single sentence, what we will do is we are going to call the tokenize for the English part. But in the English case, I don't want to use start tokens and end tokens. We're passing them all simultaneously anyways. We will have the entire English sentence. So there's no need of a start token and end token. Now for the Kannada case, I need to pass in a start token because during the generation phase, you're not going to have any Kannada word to start with. So you're going to have to inject something into the model, and that will be your start token. And I'm also going to pass in an end token as well, just to indicate this is where the sentence ends. And after that, it's just padding tokens. And so you can see that if you look at the Kannada tokenization, so we have like these 3 Kannada sentences, their corresponding numeric interpretations would look like this. This is the first sentence, this is the second sentence, and this is the third sentence. So they've all been mapped from characters to an index, an integer, from that character integer dictionary that we just created previously. And we can see that these 123s are padding tokens. This 124 over here is an end token, end of sentence, and this 0 is a start token. We can see something very similar for English too, if we wanted to try this out. Where 95 in this case is the padding token, and then we have, there's no start or end token, so it's just the padding tokens, and everything else is just characters in the sentences that you see. Now, in the last part of this video, I just wanted to very quickly just touch on masking. Now, coming to this transformer architecture, you'll see that you don't really need a typical type of masking for the encoder part. The only kind of masking you need is a padding mask, and that's just to say, hey, do not look at the padding when you are computing this loss function and upgrading gradient weights here. So don't look at the padding tokens, they mean nothing. So we might need to have like a padding mask interjected within the encoder, but then that is in this multi-head attention part. But with the decoder, you need a masked multi-head attention, which means that in the decoder, since this is the generation phase, during training, you have all of your Kannada translation data, but during inference, you don't have any of that. So you shouldn't be looking forward to what tokens you haven't generated. That's a form of data leakage, and we cannot have that. So what we would do is instead we would mask all of those tokens and say, hey, any character that comes after this current character, we don't want to look at it. We have no context to that. We only have the context to characters that come before it. And on top of this, we also have a padding mask. That is just masks that, kind of like what you mentioned in the encoder, we just should not be using in order to compute backpropagation gradient updates. Everything that I've mentioned just now can be kind of converted into look-ahead masks and padding masks for both the encoder and the decoder, and I've kind of printed all of these things out here. Now, instead of I'm using 0 that says, hey, this is not masked, and negative, and like a negative large number, or technically it's like a negative infinity that says, hey, this is masked, because eventually, if you look at the code, we're going to be passing this through a softmax function right over here. And when you do a softmax, that's essentially like an exponential function. So that's whatever is 0, it's e to the power of 0 is going to be 1, which is okay, that's pass through. But if it's a negative infinity, e to the 0 is going to be 0, which is don't pass through. So that's kind of why we use negative infinity 0 instead of like 0, 1. And I specifically do not use negative infinity and use like a very low negative number instead, because there will eventually be cases where your entire rows are just zeros. And if all your rows are zeros during a softmax, that means the output of softmax is going to do 0 by 0. This is going to lead to nans, or numerical instability. And if you get that as a nan, then the output loss is also going to be a nan, not a number. And this is just not trainable. And so I instead inject very little information into it. And this is effectively not going to change your model too much. And hence I do it here. The output of this though, and you can try this out, is that, well, you'll get an encoder self-attention mask, as zeros means that pass through, until the character that you see. And then you'll just get negative infinities. Then the decoder self-attention mask, you'll see that it's a look-ahead mask. So only the first one is 0, everything else is going to be, negative infinity. Here, only the first 2 are in the second row, only the first 2 are 0. In the third row, only the first 3 are 0, and so on. And then we have like a decoder cross-attention mask, which is kind of more similar in that it has a padding mask like the encoder self-attention mask here. I've put all of this actually together in a very cute class of a function which we call sentence embedding, where I have this wonderful set of operations that I'm going to be performing. And I also have this batch tokenization. So we have a tokenization function. Everything that I've written out, I've encapsulated in a function to handle batches of data. All right, so now that we've taken a look at a good portion of different components of how to code out the encoder, the decoder, and even parts that come before and after it, let's actually take a look at the entire transformer code end to end for the encoder and decoder. And in this case though, and we'll see that there's like 300 lines of code, I'm going to explain all of this. Although we've already done deep dives in different parts of this code separately, this section is just going to marry the two. So it's not going to be a super long section, but it will give you better context into how everything is connected with code. So let's get to it. So as a reminder, we are currently in the process of building a translator from a language called English to a language called Kannada, which is a language that's spoken in a specific state in India. And the way that we're going to generate the translation for an English sentence is we're generating one Kannada character at a time and not one word at a time or one byte pair encoding at a time, as you would see probably some other implementations do. So we pass in English sentences over here, and for each character we will get a vector that encodes some contextual meaning to it. And we'll take these vectors, pass it into the decoder architecture along with the Kannada vectors, which are transposed like by one word. There's going to be an additional start token preceding the sentence, and then we'll have during training the entire Kannada sentence but without the start token. And so in the end, this is a way to parallel train the model so that it's much faster in training. And during inference time though, we would just use the start token and pad the rest while passing it into the entire decoder architecture to generate the first Kannada word. That word is then taken and passed into the output section, whatever it says here, in order to generate the second word. And we do this until we get the end of sentence token to generate the full Kannada sentence, one character at a time. Now, with that context out of the way, we can actually look at the code. So this here is the transformer class that implements or extends the Torch modules. We have dmodel, which is going to be the dimensions for every single character vector. Typically, in this case, we take it as 512. ffhidden is the hidden layers for the feed forward layers that we see throughout the network, which is 2048. Numheads is the number of heads that we see in the multi-headed self-attention and also multi-headed cross-attention. Drop_prob is used for dropout and is the probability that we will switch off neurons to promote generalization through the network. This is typically 0.1. Num layers is the number of encoder layers as well as the number of decoder layers. And we can set this to be like 5 or something. Max sequence length is the maximum number of characters in a given input sentence, which in our case, we set it to about 200. KN vocab size is all the possible characters that can occur in the Kannada sentence or translation. Then we have English to index, which is taking a dictionary. It's a Python dictionary that maps a character to a unique number. Same thing for Kannada. And then we have a start token, end token, and padding token, which would be the start and end and padding tokens respectively. Now, during the transformer call to the forward pass, we will be taking in X, which is the English sentence, or rather, more specifically, it's the batch of English sentences. Y is the batch of target Kannada sentences. Then we have a couple of masks here. So we have the encoder self-attention mask, which is going to incorporate the padding masks. Then we have the decoder self-attention mask, which is going to incorporate both the padding mask as well as the look ahead masks. And then we have the decoder cross-attention mask, which will also incorporate the padding mask. And these 4 other parameters are going to determine whether we should include a start token and an end token to our encoder and decoder inputs and outputs. In this case, false means that we do not include it, and true means that we do. So we'll first start by taking the batch of sentences X, passing it through the encoder in order to get the list of character vectors that are eventually going to be context aware. We then take those vectors into the decoder, along with the batch of Kannada sentences, which is Y, in order to finally get the output of that decoder. And we're going to be eventually passing this into a softmax activation when we're computing the loss function. If we take a look at the encoder, so this X here as the input is going to be the batch of English sentences, we're going to construct the sentence embeddings. This is going to eventually take every single sentence. We're going to use the character. We have to map it to integer values for every single sentence and every single character in the batch. and then we're going to pass it through the encoder. And the self-attention mask is going to be just the padding mask, because we, in the English sentence, are allowed to look forward and look backwards, so we don't need that look ahead mask here. And so we're just going to get a list of contextually aware characters in the form of vectors. The decoder, on the other hand, is going to take these list of vectors X, but also the batch of input sentences Y. We're going to perform the sentence embedding. That is, we're going to perform like the tokenization of characters. And then we're also going to include, whether we include like a start token or end token. And this depends on whether it's the input to the decoder or the output of the decoder. So the input to the decoder is only going to include a start token, but the output is not going to include the start token, but it will include that end token. We then pass it through the decoder, passing in the self-attention mask and the cross-attention mask. And then we get the output, which is a set of Kannada character vectors. So that's the entire transformer neural network code. And now we want to use this code in some way. So I've put together a trainer notebook, which you can use to train a neural network. I've already gone ahead and trained it on the task of English to Kannada. We will go through that trainer notebook code step by step, and we'll also go through some fun inference translations just to see how well the transformer neural network did. So let's get started. Before I get started with this video, I wanted to give a quick shout out to this user account Tiger07, where they helped point out a specific issue where in my last training videos for building out the transformer, I kind of made some errors. They pointed out like 2 lines of code that I kind of needed to change throughout the network. And this is the line itself. It was just reshaping of these tensors, because I think it was PyTorch when I was just doing a values, like some reshape, which would have completely discombobulated all my tensors. I needed to do a permutation of some layers. It's a very minor technical issue, but it was a major one in the sense that it stalled me for a very long time. And I'm really grateful that, when I reached out to the community, you all responded very well. I also wanted to give a shout out to this account, PingNG. Sorry if I'm mispronouncing that, if anything, who recommended the same exact solution, but also detailed why that was the case. So thank you so much as well. And that just shows how well this community does respond, because even Slack nor ChatGPT could really help me out, but you all did. So thank you so much. For now, let's just go to the part where we're actually instantiating the transformer. And the only thing I really want to point out here is that we are going to use only one encoder and one decoder layer. So this is going to be the simplest of the simplest transformer neural networks, so that I could just train this faster to see some reasonable results. That's the only reason I did this. And I did this training for about 1.5 hours, where I trained it for 10 epochs, where I'll scroll here. You see that's 10 epochs with the data set of around 200,000 English sentences to translate into a language called Kannada. And all of this training epoch, I've printed out 100 epochs at a time. For now, let's get to the good part of transformer inference. So this here is a character language model where we're generating one character at a time. And so you'll see everything is going to be within a for loop, where I am generating one character at a time. You generate the token and append it to the sentence, and just keep doing this until you generate an end token, which will signify the end of a sentence. On doing so, you'll get a few examples. So let's just look at a few of them. When I say try to translate what should we do when the day starts, the translation it gives is this sentence over here, which says idara bagge ಏನು ಮಾಡಬೇಕು, which is what do we do about this? Although it doesn't translate exactly to, the sentence, at least we can kind of see that there are some commonalities that are retained, like this last 2 words over here and these last 2 words over here. It is retained in some way. So ಏನು ಮಾಡಬೇಕು, that's these 2 words. That just means what should we do? And that just corresponds to this part of the sentence. So it kind of gets a part of the sentence right, but very clearly it distorts the entire meaning, so it's not quite getting everything correctly. You can attribute this to a few cases. So the first thing is the model is just too simple. It only has one encoder and one decoder. And if you increase the number of encoder and decoder components, you probably might be able to pick up on more idiosyncrasies in language. That's probably the biggest reason, but you can also try increasing your training set or increasing the number of epochs for your training time. Now, the second sentence is, how is this the truth? The actual translation is idu hege satya, whereas this here is the generated translation, which says hege idu hege hege. So this is not really a meaningful sentence, but you can see that there are some common. Hege is generated as well, idu hege. So idu means like this, hege is how, satya is truth. So it translates to how is this the truth. So it does generate some part of it, and you can see, just by looking at these two examples, you can kind of see that it is definitely learning something, although it might not be complex enough to pick up everything about these sentences. Now, this example is my name is Ajay, which should translate to Nanna hesaru Ajay, but it translates to Nanu kutumbada hesaru. So you can see again, there are some commonalities with hesaru, which means name. Nanna is my, but Nanu it's very close to it, but it means me. It did not pick up at all on my name at all, Ajay. Also, although the overall translation is off, once again, we see some words that are actually common and correct. Now, this one's interesting. Why do we care about this? The actual translation that it gave was Eke karana eno. With punctuation, it would be like, why? What's the reason? That would be the actual translation of this, which is actually very close to the translation of this initial sentence over here. So not bad. It did pretty good there. The next is, this is the best thing ever. Whereas, here it generates this sentence, but actual translation is this sentence, which translates to this is very unusual. So though the meanings are kind of off, you can see that there are just some commonalities between them again. Now, this is probably the most interesting example throughout the lot, where I wanted to translate I am here. The actual translation is Nanu illiddene. The projected translation by the translator was Nanu keliddene. So there are different meanings. This means I am here, whereas this means I've heard something. And although there are different meanings though, you can see that from a character by character generation that this translator is performing, it's actually doing extremely well. The only thing in the translator's eyes that it got wrong was this E and this K. Like these two alphabets are like the only thing that are different in this entire translation, barring some small like la. They're both la's, but either way, just one or two characters are the only things that are wrong. So in the translator's eyes, this translation is actually a pretty good one. But this kind of made me think more about the fact that, okay, this is a character translation, but in general, word translations might actually perform better. But the caveat of using word translations is that your transformer will need to have a much larger vocabulary as opposed to what it has now. So you can see if I scroll up to see like what is the length of any possible characters that are possibly generated or tokens that are generated, you can see it's only a small set of values here, maybe like maybe 50 to 100 tokens or something like that. But if it was words, then all possible words were in this list. This entire list would explode to the tens of thousands because there can be so many words that need to be generated. So there's always this trade-off between larger vocabulary size but interpretable values. So you need like much more complex systems, like you need probably a more complex translator and also way more parameters in order to account for, words themselves. But with words though, the sentence length will technically decrease. While here I have provided like the maximum sentence length to be 200 characters, the number of words in a sentence doesn't have to be like 200 words. It could be just, a dozen or something like that we can cap it out. Now here's an interesting one too. It says click this, and this would be the translation, which is idanu click mari, which is click this. But the actual translation is kyan click 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 mari. So although it does get this last part right, click mari, and it does get it here, it just loves click 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 click. So it's just funny. But it is, once again, understanding what the task is, at least to an extent. Now, the same thing is here. Where is the mall? the translation is, well, the translation that it generated was yelly, 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 which is where. So at least it got the where part is, but it didn't generate anything else. Now, what should we do? The translation is Enu Marabeku. Now, it generated this correct, but it absolutely fumbles on this one here. Today, what should we do? This, I have no idea why it generates this. It says, Adannu maridara mele maridda maridare. So it just loves is to do. And I guess that's like a very common phrase that you see everywhere in both English and also in this language, Kannada, and that's why you're seeing like all kinds of forms. When you see like, oh, do, it probably tries to do mari like everywhere. It just tries to create this scenario, which again, very interesting, but it completely fumbles despite, in English, when we see this, it's kind of like the very same sentence as what we did before, just an extra word. So that's just, it's an interesting note. But if I phrase it as why did they do this? This sentence actually generated almost perfectly well. But again, this is something to do with doing something. So it's a very common sentence in general, or a common phrase. So that's probably why it did so well. This last part here is also a very interesting one. It's what's the word on the street? And the generated translation is idara bagge, so what is the topic of this, or what is this about, is the translation, which kind of does semantically relate to what this actually means, this little idiom here. Let's now go through some insights where I'm probably going to give you some information and some tips when building out a transformer on your own with any language. So first of all, I wanted to say create a translator with a language that you understand ideally, because it's just so much easier to see where the transformer is doing things correctly and where it's also doing things incorrectly. So generating that insight for yourself, I think, is very important. And you can better do so if you understand the language itself. So in this case, people were saying, why did you use Kannada? It's because I can understand and I can properly evaluate it. Otherwise, I wouldn't be able to come up with the insights that I did. Piggybacking off of that, here's I think a pretty important insight that I haven't really seen anywhere, but I'll describe here. So when training, typically the English character set is known as what we call an alphabet, where every character kind of has a phonetic representation to it. In a language like Kannada, it's more of an alpha syllabary. So you have individual units to actually be complete like syllables themselves. And in doing so, that means that even though, like for example, this word, I think I typed it out here. So this is a character. This is ma. Ma, if you write it out in English, it would be M-A with like, like an accent on top of it. That would be, so it's like multiple characters in English, but it's a single character in the Kannada language. However, when I was dealing with tokens here, the way that I'm tokenizing the data is I'm also treating it as like multiple tokens. So it would be m plus a. Even though in the current language it's actually supposed to be one character, I am treating it as two characters. And so what semantically just makes more sense is to create a tokenizer that will not just divvy up the entire, Kannada like word into very sub characters, but rather divvy the Kannada word into actual Kannada characters themselves, which may or may not be a combination of two or more of these characters. Also, alpha syllabaries are a type of script that are not confined to just this language, Kannada. There are many alpha syllabaries out there. And so just understanding the writing style may actually create a translator that is more meaningful. And so I highly recommend you try this out. Now, another insight that I mentioned is kind of similar to what I described before. This is generating one character at a time. So it's a smaller vocabulary, but longer sentence length. But you can play with generating like word at a time, where it'll have a much larger vocabulary, but smaller sentence length. And a good mix of both worlds is to use something called byte pair tokenizations or byte pair encodings, which are like subwords. Now, the issue with this is that it's very hard to create a byte pair encoding for certain languages if they don't, if they're not really, don't have a great research or online presence. So it's hard for me to find one for the language Kannada, and hence I went with character tokenizations for now to illustrate concepts and ideas. But if you're able to create like byte pair encodings for your languages, input and outputs, then I think that might be like a good starting point. In fact, I think this is exactly what's happening in the main paper and a lot of other research associated with generative models these days. Another one is to make sure that your training set has a large variety of words in general. You could see that above when I illustrated here. There's a lot of sentences that are like to do, right? Mari there's like a lot of these sentences that kind of go marbeku and mari over here. In fact, if you look at this data set, there's actually 10,000 cases at least of there's like millions of records here, but there's like 10,000 cases at the very least where we just have this entire word called marabeku, which is I have to do. And that's a very common phrase. So I would suggest you try to plot out every single word and their frequency counts just to get an idea of what kind of data set you're dealing with, whether it's very catered to like news, government articles, politics, or if it's catered to just like general and random sentences, which ideally would be the case for general translators. And the other one is just more technical, where you're increasing the number of encoder and decoder units, as I've only used one, keeping it very simple. But you can ideally try with more encoder-decoder units to pick up more complexities and intricacies in your languages. Overall, yeah, this model has definitely learned something, and you can use it for, other languages instead of Kannada as well. And that's going to do it for this series. So I hope that right now you have a good idea of how the transformer works, its code, its architecture, and all of the code for the entire series, along with the diagrams, are going to be in this GitHub repository, which I'll put the link to for in the description below. Once again, thank you all so much for 100K. Onwards and upwards, as the corporations say, and I will see you in another video. Bye-bye.